There is a moment frozen in time, approximately 70,000 years ago, when the entire human species stood on the knife's edge of extinction. A volcanic winter so catastrophic that it reduced our ancestors to perhaps as few as 1,000 breeding individuals, a population smaller than a modern high school. Tonight, we descend into the genetic archives written in your very DNA to reconstruct humanity's most terrifying bottleneck, a near-death experience for our entire species that left an indelible scar in our chromosomes. This journey will lead us to a single small tribe huddled somewhere in Africa, the lone flickering flame of consciousness in a world plunged into darkness and ash. We will expose the scientific evidence that proves every human alive today, all 8 billion of us, carries the genetic signature of this one group's desperate survival. The supervolcano that nearly erased us, Mount Toba, erupted with a force 5,000 times greater than Hiroshima. But the true revelation isn't just that we survived. It is the undeniable proof that this apocalyptic filter forged something new in us. A cognitive revolution, a spark of innovation and adaptability that would eventually allow this tiny remnant to not just survive, but to conquer the entire planet and become the only human species left standing. This is not a story of what might have happened. This is the reconstruction of the day we almost weren't. Every human being alive today is remarkably, almost impossibly similar at the genetic level. When scientists first mapped the human genome and began comparing populations from across the globe, they discovered something that defied expectations. The genetic diversity among all humans is astonishingly low compared to other species. 2 random chimpanzees from the same forest in Africa can be more genetically different from each other than a human from Tokyo is from a human in Sao Paulo. This peculiar homogeneity is not normal. It is the signature of something catastrophic. Our DNA tells the story of a severe population crash, a genetic bottleneck so extreme that it compressed all human diversity through the eye of an evolutionary needle, leaving behind a species that is, genetically speaking, a family of near twins scattered across continents. The revelation came gradually, puzzle piece by puzzle piece, as geneticists in laboratories around the world began sequencing DNA from thousands of individuals representing every major population group on Earth. They expected to find deep genetic divisions corresponding to geographic separation, vast chasms of difference carved by hundreds of thousands of years of isolated evolution on different continents. Instead, they found shallow pools of variation, minor ripples where they anticipated canyons. The numbers were startling and initially difficult to accept. The entire global human population exhibits less genetic diversity than a single troop of chimpanzees numbering a few hundred individuals. Let that sink in for a moment. 8 billion humans, spread across every ecosystem from the Arctic tundra to tropical rainforests, separated by oceans and mountain ranges, speaking thousands of languages, practicing countless cultures, and yet we are all variations on an incredibly narrow genetic theme. This uniformity extends to every measurable aspect of our genome. Whether examining nuclear DNA inherited from both parents, mitochondrial DNA passed down exclusively through mothers, or the Y chromosome transmitted from father to son, the story is the same. Our family tree is not a sprawling oak with ancient, divergent branches. It is more like a recently planted sapling, with all its branches emerging from a single, recent trunk. Population geneticists use a measurement called nucleotide diversity to quantify genetic variation within a species. In humans, this value hovers around 0.1%, meaning that any 2 random humans differ at only about 1 in every 1,000 DNA base pairs. Compare this to our closest living relatives. Chimpanzees, despite having a much smaller total population and geographic range than humans, have a nucleotide diversity nearly 3 to 4 times higher. Gorillas, even more critically endangered, still maintain greater genetic diversity than the entire human species. This is not a trivial statistical quirk. It is a glaring anomaly that demands explanation. The most compelling and scientifically supported explanation is that at some point in our relatively recent evolutionary past, the human population was reduced to a tiny remnant, a founding group so small that the vast majority of genetic variation that had accumulated over millions of years of hominin evolution was simply lost. The survivors of this near-extinction event became the ancestors of every person alive today, and their limited genetic diversity became the permanent ceiling for all future human variation. This is the genetic bottleneck hypothesis, and it transforms our understanding of human history from a story of steady progress to one of catastrophic survival. But what could cause such a dramatic population collapse? The Earth is a violent and unpredictable place, capable of unleashing forces that dwarf human comprehension. To understand what nearly erased us, we must look beyond the laboratory and into the deep geological record, to a specific point in time approximately 74,000 years ago, when the planet itself convulsed with a fury that blotted out the sun and plunged the world into a frozen nightmare. The genetic mirror reflects our shared past, but it also points us toward the catastrophe that forged us, a singular event that left humanity teetering on the edge of oblivion. A population bottleneck occurs when a species undergoes a dramatic reduction in numbers due to catastrophic environmental events, disease, or predation. The surviving population, now tiny, carries only a fraction of the genetic diversity that existed before the crisis. Every subsequent generation is descended from this small group of survivors, forever marked by their limited genetic palette. In evolutionary terms, it is like funneling an ocean through a garden hose. What emerges on the other side is smaller, concentrated, and fundamentally different. For humans, evidence of such a bottleneck appears in our mitochondrial DNA and Y chromosome studies, which trace unbroken maternal and paternal lineages back through time. These genetic breadcrumbs converge on a specific window approximately 50,000 to 100,000 years ago, pointing to a period when human populations collapsed to levels that should have meant extinction. The mechanics of a genetic bottleneck are brutally simple. Imagine a population of 10,000 individuals, each carrying unique combinations of genetic variants accumulated over countless generations. This population represents a rich library of genetic information, with rare variants that might prove valuable under future environmental conditions, neutral variations that add no particular advantage or disadvantage, and common variants that define the species' baseline characteristics. Now imagine that a sudden catastrophe, a plague, a climate shift, a volcanic eruption, reduces this population to just 100 survivors. Those 100 individuals carry only the genetic variants they happen to possess. Every rare variant, every unique adaptation that existed only in the 9,900 who perished, is now extinct. It doesn't matter how potentially valuable those lost genes might have been. They are gone forever, erased from the species' genetic future as completely as if they had never existed. The survivors become the new founding population, and as they slowly rebuild their numbers over subsequent generations, all of their descendants will carry only the limited genetic variation present in that tiny group. This creates a permanent genetic signature that can be detected tens of thousands of years later. The signature appears as a sudden coalescence in genealogical trees, a point where all lineages converge to a small number of ancestors in a very short time window. It is visible in the patterns of linkage disequilibrium, where genetic variants that should have been shuffled and randomized over time remain locked together because there simply wasn't enough genetic mixing to break them apart. It manifests as an overall reduction in heterozygosity, the presence of different variants at a given genetic location across the entire genome. For human populations, this bottleneck signature is unmistakable and deeply etched into our chromosomes. The mitochondrial DNA evidence is particularly striking. Mitochondria, the energy-producing organelles in our cells, carry their own small circular genome separate from the DNA in the cell nucleus. Because mitochondria are inherited exclusively from the mother, with no genetic contribution from the father, they provide a clean, unbroken maternal lineage stretching back through time. When geneticists constructed a family tree using mitochondrial DNA from thousands of people representing all human populations, they discovered that every branch, every twig, every leaf on that tree traced back to a common trunk that existed sometime between 150,000 and 200,000 years ago in Africa. This most recent common ancestor on the maternal line has been named Mitochondrial Eve, though this name is somewhat misleading. She was not the only woman alive at her time, nor was she the first human female. She is simply the woman whose direct maternal line, through an unbroken chain of daughters, survived to the present day, while all other contemporary maternal lines eventually died out. The same pattern emerges when examining the Y chromosome, which passes from father to son. All human Y chromosomes trace back to a single man, Y chromosomal Adam, who lived roughly 200,000 to 300,000 years ago. Again, he was not the only man alive, but he is the one whose paternal line persisted. The convergence of these lineages, along with evidence from the rest of the genome, points to a dramatic narrowing of the human population sometime after these common ancestors lived. The genetic data suggests that around 70,000 years ago, the effective breeding population of humans may have dropped to as few as 1,000 to 10,000 individuals. These are numbers that place a species on the endangered list, numbers from which recovery is uncertain and extinction is a very real possibility. Something catastrophic happened to humanity in that window of time. Something that brought us to the very brink of annihilation and left an indelible scar in our DNA. Approximately 74,000 years ago, in what is now northern Sumatra, Indonesia, the Earth's crust ruptured in one of the most violent volcanic eruptions in the last 2 million years. Mount Toba, a supervolcano, exploded with an estimated volcanic explosivity index of 8, the highest rating on the scale. The eruption ejected an estimated 2,800 cubic kilometers of volcanic material into the atmosphere, enough to bury the entire United Kingdom under 12 meters of ash. The explosion was so powerful that it created a caldera, a massive crater, that today holds Lake Toba, one of the largest volcanic lakes on Earth. The sound of the eruption would have been heard across half the planet. The immediate blast radius was a zone of total annihilation, but the true killer was yet to come, carried on the winds. To understand the magnitude of what occurred, we must first understand what a supervolcano actually is. Unlike the iconic cone-shaped mountains we typically associate with volcanic activity, a supervolcano is a geological monster of an entirely different order. It forms when a massive chamber of molten rock or magma accumulates deep beneath the Earth's surface, sometimes stretching across hundreds of square kilometers. This chamber builds pressure over hundreds of thousands of years as fresh magma continues to rise from the mantle. Below, inflating like a colossal balloon of liquid fire, the overlying crust becomes thinner and more stressed, eventually fracturing in a catastrophic release that dwarfs anything witnessed in recorded human history. Mount Toba had been building toward this moment for millennia, a ticking geological time bomb beneath the lush tropical forests of Southeast Asia. The eruption itself would have begun with a series of increasingly violent earthquakes as the magma forced its way upward through weakening rock. Early humans living within hundreds of kilometers would have felt the ground shaking, perhaps seen steam and small eruptions as groundwater came into contact with the rising heat. Then, in an instant that forever divided geological time, the entire roof of the magma chamber collapsed. What followed was an explosion of such incomprehensible violence that it redefined the very landscape. Superheated rock and gas, compressed under unimaginable pressure, was hurled into the atmosphere at supersonic speeds. Pyroclastic flows, avalanches of gas, ash, and pulverized rock heated to over 700 degrees Celsius raced outward from the collapsing caldera at speeds exceeding 100 kilometers per hour. Everything within a 100-kilometer radius was instantly incinerated. Trees, animals, any humans unfortunate enough to be within that zone, all were vaporized or carbonized in seconds. Their remains buried under tens of meters of volcanic debris that would later solidify into rock. But the immediate destruction, as horrific as it was, represented only a tiny fraction of Toba's killing power. The true catastrophe was atmospheric and global. The eruption column, a towering plume of ash, gas, and pulverized rock, punched through the troposphere and penetrated deep into the stratosphere, reaching heights estimated at 50 kilometers or more. This is 3 times higher than commercial aircraft fly, well into the realm where the air is too thin to breathe and the temperature plummets to minus 50 degrees Celsius. At these altitudes, the volcanic material began its deadly dispersal. Prevailing stratospheric winds, which circle the globe at high speeds, caught the ash and aerosols and spread them east and west in an ever-expanding veil. Within weeks, the ash cloud had encircled the earth, a shroud of darkness that dimmed the sun and began the slow suffocation of the biosphere. The geological evidence for this event is preserved in layers of ash found across the Indian Ocean, South Asia, and East Africa. Drill cores taken from the ocean floor reveal a distinct layer of Toba ash, chemically fingerprinted to the eruption, spread across millions of square kilometers. On land, the ash deposits are even more dramatic. In parts of India and Malaysia, the ash layer is several meters thick, a gray testament to the sky's fury. This was not a local disaster. It was a planetary trauma, an event so massive that it reset ecosystems across continents and created the environmental conditions for a mass die-off of species. And somewhere in Africa, small bands of early humans, unaware of the distant explosion that had just occurred, were about to face the fight of their lives. Within hours of the eruption, a colossal plume of superheated ash, rock, and sulfur dioxide rocketed into the stratosphere, piercing through the troposphere and dispersing across the upper atmosphere. This was not ordinary volcanic ash. It was a dense mixture of pulverized rock, toxic gases, and sulfuric aerosols that spread like a dark veil across the sky. Prevailing winds carried the ash eastward and westward, blanketing South Asia, the Indian Ocean, and eventually reaching as far as East Africa and the Arabian Peninsula. Archaeological sites thousands of kilometers from Toba contain layers of volcanic ash from this single event, a gray stratum that marks a moment of global catastrophe. The ash fall in India alone measured up to 6 meters deep in some regions, smothering entire ecosystems beneath a sterile, suffocating blanket. The initial ash fall would have been terrifying for any humans who witnessed it. Imagine standing under an open sky that suddenly begins to darken at midday, not with the familiar gray of storm clouds, but with an unnatural, ominous dimming. Then the ash begins to fall, not as gentle snowflakes, but as a relentless rain of gritty, abrasive particles. that sting the eyes, clog the nose and throat, and coat everything in a thick gray powder. This ash was not like the soft dust that settles after a sandstorm. It was composed of microscopic shards of volcanic glass, sharp-edged fragments of pulverized rock that could lacerate lung tissue with each breath. For humans caught in the heaviest ashfall zones across South and Southeast Asia, survival would have required immediate action. Shelter became critical, not just to escape the falling ash, but to avoid the toxic gases that accompanied it. Hydrogen sulfide and sulfur dioxide that turned the air acrid and poisonous. As the ash accumulated on the ground, it transformed the landscape into an alien, lifeless wasteland. Plants that managed to survive the initial deluge were buried and suffocated, unable to photosynthesize under the gray shroud. Water sources became contaminated, choked with ash that turned rivers and lakes into thick, undrinkable sludge. The ash was also highly acidic, further poisoning any water it touched. Animals that depended on grazing found nothing but ash-covered ground. Those that depended on those grazers began to starve. The food chain collapsed from the bottom up with devastating speed. Archaeological evidence supports this nightmare scenario. Excavations in India have uncovered the Toba ash layer at numerous sites, and what is most striking is what appears immediately above and below it. Below the ash, there is evidence of rich, diverse ecosystems and active human occupation with stone tools and signs of daily life. Above the ash, there is often a stark gap, a period where evidence of human activity disappears entirely or is drastically reduced, suggesting that populations either fled, died, or were so diminished that they left virtually no trace. But the atmospheric impact extended far beyond the regions that received direct ashfall. The stratospheric component of the eruption, the portion that climbed highest and spread furthest, contained billions of tons of sulfur dioxide. This gas, once injected into the stratosphere, underwent a transformation that would alter the global climate for years to come. High above the Earth, sulfur dioxide molecules reacted with water vapor and oxygen to form tiny droplets of sulfuric acid. These droplets, each only a fraction of a micron in diameter, do not fall back to Earth quickly. Instead, they remain suspended in the stratosphere for years, forming a reflective aerosol layer that encircles the planet. This layer acts like a mirror, reflecting incoming solar radiation back into space before it can warm the Earth's surface. The result is a dramatic and rapid global cooling event known as a volcanic winter. The beauty and terror of this process lie in its efficiency. Unlike ash, which falls out of the atmosphere relatively quickly, these sulfuric acid aerosols persist, continuously blocking sunlight day after day, month after month. Climate models that simulate the Toba eruption suggest that within weeks of the eruption, global temperatures began to drop. Within months, the cooling became severe. The sulfuric veil had transformed the sun from a life-giving star into a pale, distant disk, barely visible through the haze. The warmth that had sustained ecosystems across the planet was being stolen away, replaced by an encroaching cold that would grip the Earth for years and push countless species, including our own, toward the edge of extinction. The sulfur dioxide ejected into the stratosphere underwent a deadly transformation. High above the Earth, it combined with water vapor to form billions of tiny sulfuric acid droplets, creating a reflective aerosol layer that encircled the planet. This reflective shield had a devastating effect. It bounced incoming solar radiation back into space, drastically reducing the amount of sunlight reaching the Earth's surface. Global temperatures plummeted. Some climate models suggest an average drop of 3 to 5 degrees Celsius worldwide. with regional drops in the northern hemisphere potentially reaching 10 to 15 degrees. This was the onset of a volcanic winter, a prolonged period of cold and darkness. Photosynthesis slowed or stopped. Plants withered and died. The cascade of ecological collapse had begun, and at the top of the newly fragile food chain, early humans faced annihilation. The cooling did not arrive gradually, giving ecosystems time to adapt. It came with shocking speed. Within a single growing season, temperatures that had been warm enough to support lush vegetation dropped to near freezing levels even in tropical regions. For plants, this was catastrophic. Photosynthesis, the fundamental process that converts sunlight into chemical energy and forms the base of nearly all food webs, requires both light and warmth. With the sun dimmed to a fraction of its normal intensity and temperatures plummeting, plants began to shut down. Leaves that had been green and vibrant turned brown and fell. Seasonal plants failed to complete their life cycles, producing no seeds for the next generation. Perennial plants went dormant or simply died, unable to survive the prolonged cold. Across vast stretches of the planet, forests that had stood for thousands of years began to wither. Their canopies thinning as trees succumbed to the stress, the impact rippled upward through every level of the food web with brutal efficiency. Herbivores, from insects to massive megafauna, found their food sources disappearing. Grasslands that had supported herds of grazing animals turned into barren expanses of dead vegetation and exposed soil. Browsers that fed on leaves and shoots found skeletal trees with nothing to offer. Starvation set in quickly. Young animals, already vulnerable, died first. Then the adults, weakened by hunger and cold, began to fall. Predators that depended on these herbivores soon followed. With prey populations crashing, carnivores faced a terrible choice: expand their territories in search of dwindling food, which meant expending precious energy in a time of scarcity, or starve. Many chose neither and simply perished where they stood, their bodies adding to the growing toll of the volcanic winter. For early humans, the situation was equally dire but complicated by our unique ecological niche. Unlike specialized predators that depended on a single prey species or herbivores that relied on specific plants, humans were generalists. Our ancestors ate a wide variety of foods: fruits, nuts, roots, tubers, small game, large game, insects, fish, and shellfish. This dietary flexibility had been one of our greatest evolutionary advantages, allowing us to thrive in diverse environments. But when the volcanic winter struck, this advantage was neutralized. It did not matter that humans could eat many different things when almost nothing was available to eat. The fruit trees bore no fruit. The nut trees produced no nuts. The tubers in the ground rotted or failed to grow. The game animals were dying or had already fled to regions that might still support them. The rivers and lakes, choked with ash and suffering from the cold, saw their fish populations decline. The psychological impact on human survivors would have been profound. These were people who understood their environment intimately, who knew the seasonal rhythms of plant growth and animal migration, who had developed sophisticated knowledge passed down through generations about where to find food and water. Suddenly, that knowledge became useless. The world they knew, the reliable patterns that had sustained their ancestors, had been shattered. Imagine the terror of watching your children grow thin and weak, of searching desperately for food and finding nothing, of seeing elders, the keepers of knowledge and wisdom, dying because there was simply not enough to eat. The social fabric of human groups would have been tested to its limits. Bands that had lived in relative proximity might have been forced to compete for the same dwindling resources, leading to conflict. Alternatively, the crisis might have forced unprecedented cooperation, with groups pooling their knowledge and resources to survive. The volcanic winter also brought secondary effects that compounded the misery. With temperatures dropping, water that had been liquid froze, making hydration difficult in regions that experienced severe cold. Hypothermia became a constant threat, especially at night. Humans needed fire more than ever, not just for warmth, but to make certain plant materials edible through cooking, breaking down toxins that would otherwise be deadly. But gathering firewood in a dying forest, where every other desperate creature was doing the same, was a challenge. The Toba eruption had not just changed the climate. It had rewritten the rules of survival, and humanity was forced to adapt or face extinction. The volcanic winter triggered by Toba was not a brief, cold snap. Evidence suggests it may have lasted for 6 to 10 years at its most intense, followed by decades of cooler than normal temperatures and disrupted weather patterns. Forests that once teemed with life turned into gray, skeletal landscapes. Grasslands that supported vast herds of herbivores became barren wastelands. The herbivores, unable to find food, starved in massive numbers. The predators that depended on them followed suit. Bodies piled up and decomposed slowly in the cold. For early humans, who were hunter-gatherers relying on a diverse array of plants, fruits, nuts, and game animals, this was a death sentence. The carefully balanced ecosystems they had adapted to over hundreds of thousands of years disintegrated in the span of a single generation. The collapse was not uniform across the planet, but its fingerprints were everywhere. In Africa, savanna ecosystems that had supported a rich diversity of megafauna began to fragment. Elephants, which require enormous quantities of vegetation daily, faced starvation as grasslands failed to regenerate. Antelope herds, normally numbering in the thousands, dwindled to scattered groups desperately searching for any patch of surviving grass. The great cats, lions, and leopards found fewer and fewer prey animals, and their populations crashed in turn. Scavengers like hyenas and vultures, which typically fed on the kills and carcasses left by predators, found the supply drying up as even the predators themselves began to starve. The intricate web of dependencies that had evolved over millions of years unraveled in what must have seemed like the blink of an eye to those living through it. In Europe and Asia, where the cold was even more severe, the devastation was total in many regions. Temperate forests, already adapted to seasonal cold, could not withstand the extended freeze and perpetual dimness. Deciduous trees that normally dropped their leaves in winter and regenerated in spring found no spring coming. Evergreens, stressed by the cold and lack of light, became vulnerable to disease and insect infestations. Entire forests died standing, creating vast graveyards of dead timber that would later become tinderboxes when conditions eventually warmed and dried. The large herbivores of these regions, species like the woolly rhinoceros, giant deer, and various species of wild horses, depended on the productivity of these forests and the grasslands at their edges. As their food sources vanished, so did they. Not immediately, but through a slow, agonizing process of population decline that saw birth rates plummet and mortality rates soar. The marine ecosystems were not spared either. While the oceans act as a buffer against rapid temperature changes, the reduction in sunlight penetrated the surface waters, affecting phytoplankton, the microscopic photosynthetic organisms that form the base of the marine food web. With less sunlight, phytoplankton productivity declined, which in turn affected the zooplankton that fed on them, and then the small fish that fed on the zooplankton, and so on up the chain to the large predatory fish, marine mammals, and seabirds. Coastal human populations that depended on fishing and shellfish gathering would have seen their catches diminish, adding another layer of stress to their survival. The decomposition of the vast numbers of dead animals and plants created its own set of problems. In normal times, decomposition is a vital ecological process, returning nutrients to the soil and supporting new growth. But the sheer volume of death overwhelmed the system. Decomposer organisms, bacteria, and fungi could not keep pace, especially in the cold conditions that slowed their metabolic processes. Carcasses accumulated, creating breeding grounds for disease. Pathogens that might normally be kept in check by healthy, robust populations found weakened hosts easy to infect. Epidemics likely swept through the surviving animal populations, including humans, adding disease to the already deadly combination of starvation and cold. The disruption to weather patterns added yet another dimension of chaos. The aerosol layer in the stratosphere did not just cool the planet. It altered atmospheric circulation. Monsoon systems, which billions of organisms depended on for seasonal rains, weakened or shifted. Regions that normally received life-giving rains experienced droughts. Other areas saw unusual precipitation patterns, perhaps receiving snow and ice in places that had never experienced it before. This unpredictability made it impossible for any species to anticipate and prepare for seasonal changes. The fundamental, reliability of the environment, the bedrock upon which all life depends, had been shattered. For early humans, this meant that even the survival strategies that had worked for their parents and grandparents were now useless. They were living in a new world, one that was hostile, unpredictable, and unforgiving, and they had to invent new ways to survive in it or perish. Before the Toba eruption, early Homo sapiens had been slowly spreading out from their African homeland. Fossil and genetic evidence suggests that by 100,000 years ago, small groups had begun to explore the edges of the continent, venturing into the Middle East and possibly beyond. The global human population was already small by modern standards, perhaps numbering in the hundreds of thousands to low millions, spread thinly across vast territories. These were anatomically modern humans, possessing the same brain size and physical capabilities as people today. But their cultures were relatively simple. They used stone tools, controlled fire, and lived in small, mobile bands. They were survivors, adapted to the African climate and its rich biodiversity. But they were about to face a test unlike anything their species had ever encountered. A global environmental catastrophe that would push them to the very brink of extinction. The humans living 74,000 years ago were not primitive in their cognition or capability. Their brains were just as large and complex as ours, wired with the same potential for language, abstract thought, and innovation. But they lived in a world vastly different from our own. One where survival depended on intimate knowledge of the natural environment and the ability to read the subtlest signs of seasonal change, animal behavior, and plant cycles. They were masters of their domains, skilled hunters who could track prey for days, expert gatherers who knew which plants were edible and which were poisonous, and which could be made safe through careful preparation. They had developed sophisticated social structures, living in extended family groups that shared resources, knowledge, and child-rearing responsibilities. These bands likely numbered between 20 and 50 individuals, small enough to remain mobile and avoid depleting local resources, but large enough to defend territories and accomplish complex tasks like coordinated hunts. Their toolkit, while simple by our standards, represented hundreds of thousands of years of cumulative cultural evolution. They crafted stone hand axes, scrapers, and projectile points with remarkable precision. each blow struck to flake off a piece of stone, requiring deep understanding of the material's properties and the geometry of fracture. They had mastered fire, that transformative technology that extended the day into night, provided warmth and protection from predators, and allowed them to cook food, making nutrients more accessible and eliminating toxins. Fire was also a social anchor, a gathering place where stories were told, knowledge was transmitted, and bonds were strengthened. They likely created simple shelters from branches, leaves, and animal hides. And they knew how to read the landscape to find water, shelter, and seasonal food sources. Fossil evidence from sites like Jebel Irhoud in Morocco, Omo Kibish in Ethiopia, and Herto in the Middle Awash Valley of Ethiopia confirms that anatomically modern humans had emerged in Africa by at least 300,000 years ago. By the time Toba erupted, these populations had diversified and spread across the African continent, from the Mediterranean coast in the north to the southern tip of the continent. Some groups had even ventured beyond Africa. The Skul and Kafze caves in modern-day Israel contain fossils of Homo sapiens dated to around 100,000 to 120,000 years ago. Evidence of an early, though possibly unsuccessful, expansion into the Levant. These early explorers may have been driven by curiosity, population pressure, or simply the opportunistic exploitation of new territories during favorable climatic windows. Despite their wide distribution, the total human population remained small and vulnerable. Unlike modern humans, who live in permanent settlements and rely on agriculture to support dense populations, these early Homo sapiens were entirely dependent on wild resources. A successful hunter-gatherer lifestyle requires large territories. A single band might need to range over hundreds of square kilometers to find sufficient food throughout the year. This meant that population density was inherently low. Estimates based on ethnographic studies of modern hunter-gatherer societies suggest densities of perhaps one person per 10 square kilometers in favorable environments, and much lower in marginal ones. Applied globally, this translates to a total human population likely measured in the hundreds of thousands, not millions. This small, dispersed population was highly vulnerable to any major environmental disruption. There were no food stores to fall back on, no trade networks to import resources from unaffected regions, no centralized governments to coordinate relief efforts. Each band was largely on its own, dependent on the local environment for survival. When Toba erupted and the volcanic winter began, these scattered human populations faced an existential crisis. Those in Asia, closest to the eruption and directly in the path of the ashfall, were likely wiped out entirely within months. Those in other parts of the world faced a more prolonged nightmare, watching as their familiar landscapes died around them and the resources they depended on vanished. The global human population, already small, began to collapse toward a critical threshold where recovery would become nearly impossible, and extinction a very real possibility. While Toba's immediate devastation was most severe in Southeast Asia and the Indian subcontinent, its global effects were inescapable. However, evidence suggests that one region may have been slightly more resilient: equatorial East Africa. This area, possibly including parts of modern-day Kenya, Tanzania, and the Horn of Africa, may have served as a refugium, a safe haven during the volcanic winter. The reasons are geographic and climatic. Equatorial regions are buffered by more consistent solar energy, even when diminished. Proximity to large freshwater sources like Lake Victoria and the Rift Valley lakes would have provided stable water supplies. Microclimates created by elevation changes and vegetation pockets could have sheltered small populations. It is here, in this isolated refuge, that genetic evidence points to the survival of a small founding population, perhaps as few as 1,000 to 10,000 individuals, the ancestors of every person alive today. The Great Rift Valley, stretching from the Red Sea in the north to Mozambique in the south, is a geological marvel. A massive tear in the Earth's crust where tectonic forces have been slowly pulling Africa apart for millions of years. This process has created a landscape of extraordinary diversity. Towering volcanic peaks, deep valleys, fertile plains, and a chain of freshwater lakes that serve as oases in an otherwise challenging environment. During the Toba volcanic winter, this diversity became a lifeline. While much of the planet suffered uniform devastation, the Rift Valley's varied topography created numerous microclimates, small pockets where conditions remained marginally more favorable than the surrounding regions. A sheltered valley facing north might retain slightly more warmth. A lake shore with hot springs might provide a refuge from the freezing temperatures. Highland forests at certain elevations might experience less severe ash deposition or benefit from orographic rainfall patterns that persisted even as global weather systems collapsed. These microclimates were not paradises. They were simply less terrible than everywhere else. But in a world pushed to the brink, less terrible was enough. The human populations that found themselves in these refugia faced brutal conditions. But they had one critical advantage: water. The lakes of the Rift Valley, fed by deep groundwater sources and seasonal rains, provided reliable hydration even as other water sources across the planet froze or became contaminated with ash. Lake Malawi, Lake Tanganyika, and Lake Victoria, three of the largest and deepest lakes in the world, are ancient bodies of water that have persisted through multiple climate fluctuations. Their sheer size and depth made them resistant to the rapid environmental changes that destroyed smaller ecosystems. Fish populations in these lakes, while stressed, likely survived in sufficient numbers to provide a crucial protein source for the humans living along their shores. The evidence for this East African refugium comes from multiple scientific disciplines. Genetic studies consistently point to East Africa as the location where human genetic diversity, while reduced, was preserved through the Bottleneck. Archaeological sites in this region show continuity of occupation through the period when Toba erupted, with stone tool technologies persisting and evolving rather than disappearing entirely as they did in many other parts of the world. Paleoclimatic reconstructions based on sediment cores from the Rift Valley lakes suggest that while temperatures dropped and conditions became harsher, the region did not experience the catastrophic collapse seen in higher latitudes or areas directly impacted by heavy ashfall. Life in the refugium would have been a daily struggle for survival. The human bands that endured were likely pushed to the absolute limits of their adaptability. They would have been forced to exploit every possible food source, no matter how marginal or unpalatable. Roots and tubers that required extensive processing to remove toxins, insects and grubs that could be found beneath tree bark, scavenged carcasses of animals that had died from starvation, all would have been consumed. The social bonds within these groups would have been tested to the breaking point. Sharing scarce resources is one of the defining features of human societies. But when resources become so scarce that sharing means everyone starves, the calculus becomes agonizing. Some groups may have fragmented, with individuals or families striking out on their own in desperate searches for food, most likely perishing in isolation. Other groups may have maintained cohesion through sheer force of will, enforced cooperation, or deeply ingrained cultural norms that prioritize the collective over the individual. The size of the surviving population is a matter of intense scientific debate. Genetic models suggest an effective breeding population, the number of individuals actually contributing genes to the next generation. Of as few as 1,000 to 3,000 individuals during the bottleneck's most severe phase. The actual population may have been somewhat larger, perhaps 10,000 to 15,000, when including children, the elderly, and those who did not reproduce. These numbers are staggeringly small. To put them in perspective, modern conservation biologists consider a species critically endangered when populations fall below 2,500 mature individuals. Humanity, during the Toba bottleneck, was on the knife's edge of extinction, a remnant population clinging to survival in a handful of favorable locations within the African refuge. Mitochondrial DNA, passed down exclusively through the maternal line, has allowed scientists to trace the lineage of all living humans back to a single woman who lived in Africa approximately 150,000 to 200,000 years ago. She is known as Mitochondrial Eve. Similarly, the Y chromosome, passed from father to son, traces back to a single man, Y chromosomal Adam, who lived roughly 200,000 to 300,000 years ago. These individuals were not the only humans alive at their time, nor were they a couple. They are simply the individuals whose direct maternal or paternal lines survived unbroken to the present day. The Toba bottleneck is one proposed mechanism that could explain why these lineages narrowed so dramatically. The catastrophic population crash eliminated countless other genetic lines, leaving only the descendants of these few to repopulate the world, carrying their mitochondrial and Y chromosome signatures as permanent markers of survival. The concept of mitochondrial Eve and Y chromosomal Adam is often misunderstood, conjuring images of a biblical first couple alone in a garden. The reality is far more nuanced and scientifically fascinating. Mitochondrial Eve was not the first woman, nor was she the only woman alive during her lifetime. She lived among a population of thousands of other women, each with their own mitochondrial lineages stretching back through countless generations. What makes her special, what earns her this designation, is simply that her maternal line never broke. She had daughters, and those daughters had daughters, in an unbroken chain that continues to this day in every living human. All the other women who lived alongside her either had no children, had only sons, or their daughters eventually had only sons or no children, causing their mitochondrial lineages to terminate. Over time, through this process of lineage extinction, all competing mitochondrial lines died out, leaving only the descendants of this one woman. The same principle applies to Y chromosomal Adam. He was one of many men living hundreds of thousands of years ago, but his paternal line persisted while all others eventually ended. Perhaps his sons were particularly successful, surviving to adulthood and fathering many children of their own. Perhaps it was pure chance, the random lottery of who lives, who dies, and who passes on their genes. What matters is that today, every human male carries a Y chromosome that descends directly from this single ancestral man. The fact that Y chromosomal Adam lived tens of thousands of years before mitochondrial Eve might seem paradoxical, but it simply reflects the different dynamics of male and female reproduction and the randomness of lineage survival over deep time. The Toba catastrophe provides a compelling framework for understanding why these lineages converged so dramatically. Before the eruption, human populations across Africa and beyond would have carried a wide diversity of mitochondrial and Y chromosome lineages, each representing a different maternal or paternal family tree. When the volcanic winter struck and populations crashed, the vast majority of these lineages were eliminated. Not because they were inferior, but simply because the individuals carrying them did not survive or did not have children who survived. The handful of people who made it through the bottleneck, clustered in refugia like East Africa, carried only a small subset of the original genetic diversity. As these survivors slowly repopulated the world, their lineages became the only lineages. The mitochondrial and Y chromosome family trees, which had once been bushy and diverse, were pruned down to single surviving branches. Geneticists can calculate the timing of these common ancestors by analyzing mutations, random copying errors that accumulate in DNA at relatively predictable rates. Mitochondrial DNA and the Y chromosome mutate slowly, which makes them excellent tools for tracing deep ancestry. By comparing the number of mutations between different individuals or populations, scientists can estimate how long ago they shared a common ancestor. When this molecular clock is applied to global human populations, the results consistently point to common ancestors living in Africa within the time frame that brackets the Toba eruption. The mitochondrial data points to a coalescence around 150,000 to 200,000 years ago, with a significant narrowing of diversity around 70,000 years ago, precisely when Toba erupted. The implications are profound. Every person alive today, regardless of where they live or what they look like, carries in their cells the genetic legacy of these ancient survivors. Your mitochondria, the tiny power plants in each of your cells, contain DNA that is a nearly perfect copy of the DNA carried by mitochondrial Eve. If you are male, your Y chromosome is a nearly perfect copy of the one carried by Y chromosomal Adam. Mutations have occurred over the intervening millennia, creating the variation we see today, but the core sequence remains remarkably consistent. This is the genetic proof of our shared origin, the molecular evidence that we are, quite literally, one family. The Toba bottleneck did not just reduce our numbers, it funneled all of human genetic diversity through a tiny group of individuals, forever linking every person on Earth to those ancient survivors who refused to let the fire of humanity go out. How do scientists date these ancient genetic events? The answer lies in the concept of the molecular clock. DNA mutates at a relatively predictable rate over generations. By comparing the number of genetic differences between individuals or populations, scientists can estimate how long ago they shared a common ancestor. This is not a perfect clock. It ticks at different rates depending on the gene and environmental pressures, but it provides a powerful tool for reconstructing deep history. When researchers apply the molecular clock to human mitochondrial DNA and Y chromosome data, the timelines converge on a critical period between 50,000 and 100,000 years ago, precisely the window when the Toba eruption occurred. The genetic evidence, like the geological ash layers, points to a singular, world-altering event that reset the human population counter to nearly zero. The molecular clock is one of the most elegant concepts in modern biology, transforming DNA from a static blueprint into a historical record. Every time a cell divides and copies its DNA, there is a small chance of error. Most of these mutations are neutral, neither helping nor harming the organism, and they simply accumulate over time like dust on an old book. Because these neutral mutations occur at a roughly constant rate, they serve as a kind of timekeeper. If two individuals differ by 10 mutations in a particular stretch of DNA, and we know that one mutation occurs every 1,000 generations on average, we can estimate that they shared a common ancestor about 10,000 generations ago. Multiply that by the average generation time for humans, roughly 25 to 30 years, and we can translate genetic distance into calendar years. The application of the molecular clock to human populations began in earnest in the 1980s, with the pioneering work of Alan Wilson and his colleagues at the University of California, Berkeley. They focused on mitochondrial DNA because it has several properties that make it ideal for evolutionary studies. It is small, only about 16,500 base pairs compared to the 3 billion base pairs of the nuclear genome, making it easier to sequence. It mutates relatively quickly, providing enough variation to distinguish between closely related populations. And crucially, it is inherited maternally, passed from mother to all her children without any mixing from the father, creating a clean, unbroken lineage through time. When Wilson's team sequenced mitochondrial DNA from women representing diverse global populations, they made a shocking discovery. All the sequences could be traced back to a common ancestor who lived in Africa around 200,000 years ago. This finding revolutionized our understanding of human origins. At the time, there was vigorous debate about whether modern humans evolved independently in different parts of the world from local populations of archaic humans, the multi-regional hypothesis, or whether we all descended from a single African origin. The mitochondrial clock provided strong evidence for the latter, showing that our most recent common ancestor was African and relatively recent. Subsequent studies using nuclear DNA and the Y chromosome confirmed and refined these findings, consistently pointing to an African origin and a severe population bottleneck sometime after our species first appeared. But the molecular clock is not without its challenges and controversies. Mutation rates can vary between different lineages and different parts of the genome. Factors like generation time, metabolic rate, and even environmental stressors like UV radiation can influence how quickly mutations accumulate. This means that calibrating the clock requires careful validation using independent evidence. Paleontologists provide one crucial calibration point through fossils with known ages. If we find a fossil of a common ancestor of two species and can date it to, say, 5 million years ago, we can use the number of genetic differences between those species to calculate the mutation rate and refine our clock. Archaeological evidence, like the timing of major human migrations that left clear physical traces, provides another set of calibration points. When these calibrations are applied to human genetic data, the timings become remarkably consistent. The mitochondrial clock points to mitochondrial Eve living between 150,000 and 200,000 years ago. The Y chromosome clock places Y chromosomal atoms slightly earlier, between 200,000 and 300,000 years ago. But more importantly for our story, the genetic data also reveals a dramatic reduction in diversity, a signal of a severe bottleneck occurring around 50,000 to 80,000 years ago. This is precisely the time frame of the Toba eruption, dated through radiometric analysis of the volcanic ash itself to 74,000 years ago. The convergence of the genetic clock and the geological evidence is striking and deeply suggestive. Different research groups using different methods and different populations have arrived at similar conclusions, strengthening the case that something catastrophic happened to humanity around this time. Some studies examine the patterns of linkage disequilibrium, the way certain genetic variants are inherited together, which can reveal how recently populations went through a bottleneck. Others look at the overall level of heterozygosity, the presence of two different versions of a gene, which decreases dramatically after a population crash. Still others use sophisticated computer models to simulate different demographic histories and see which one best matches the observed genetic patterns. Time and again, these approaches point to a small founding population, a near-extinction event centered on the Toba timeframe. The molecular clock has allowed us to read the scars written in our genome and reconstruct the story of our species' darkest hour. Not all scientists agree that Toba caused a human bottleneck. The Toba catastrophe theory, popularized by anthropologist Stanley Ambrose in the 1990s, has faced rigorous scrutiny and debate. Some researchers argue that the evidence for a severe population crash is not definitive. They point to archaeological sites in India and Africa that show continuous human occupation before, during, and after the Toba event, suggesting that some populations may have weathered the crisis without collapsing. Others propose alternative explanations for the genetic bottleneck, such as repeated smaller population crashes caused by climate fluctuations during the Ice Age, or geographic isolation that naturally limited gene flow. The scientific debate is vigorous, with new evidence constantly emerging. Ice core data, fossil records, and advanced genetic modeling are all being deployed to test the Toba hypothesis, making this one of the most actively researched questions in human evolutionary history. The skeptics raise important and valid points that deserve serious consideration. One of the strongest challenges to the Toba catastrophe theory comes from the archaeological record itself. If the eruption had truly caused a near-extinction event for humanity, we would expect to see a clear break in the archaeological evidence, a layer where human activity stops or becomes drastically reduced. Yet several key sites tell a different story. In southern India, for example, excavations at sites like Jwalapuram have revealed stone tools both below and above the Toba ash layer, with no apparent change in the technology or the intensity of occupation. The tools found above the ash are virtually identical to those found below, suggesting that the same population or cultural group continued to inhabit the area through the eruption and its aftermath. If the local population had been wiped out, the skeptics argue, we would expect to see either an abandonment of the site or the arrival of a new population with different tool-making traditions. Similarly, in Africa, some archaeological sites show continuity of occupation through the period when Toba erupted. While the evidence is less direct, since there is no ash layer to serve as a marker in most African sites, the tool technologies and settlement patterns do not show the catastrophic disruption that a population crash should produce. Critics of the Toba hypothesis argue that if humans were reduced to a few thousand individuals huddling in isolated refugia, we should see a dramatic simplification or regression in their material culture, a loss of knowledge and skills as populations fragmented and cultural transmission broke down. Instead, they see continuity and even gradual complexity, suggesting that populations remain stable enough to maintain and transmit their cultural knowledge. Climate scientists have also questioned the severity and duration of the volcanic winter. While there is no doubt that Toba was a massive eruption, some climate models suggest that its global impact may have been less severe than initially proposed. These models point out that volcanic aerosols, while effective at cooling the planet in the short term, are also relatively short-lived in the stratosphere, typically persisting for only a few years before settling out. Some simulations suggest that temperatures may have dropped sharply for 3 to 5 years, but then recovered relatively quickly, rather than remaining depressed for a decade or more. If the volcanic winter was shorter and less severe, it might have caused regional hardships and temporary population declines, but not the near-total collapse required to explain the genetic bottleneck. Another alternative explanation for the genetic bottleneck focuses on the broader context of the Ice Age. The period from 200,000 to 50,000 years ago was characterized by extreme climate instability, with the planet oscillating between glacial and interglacial periods. Each glacial advance would have locked up vast amounts of water in ice sheets, lowering sea levels, drying out continental interiors, and shrinking habitable zones. Each of these swings could have caused significant human population declines. Over tens of thousands of years, these repeated crashes, even if individually less severe than Toba, could have cumulatively produced the same genetic signature, a progressive winnowing down of genetic diversity through serial bottlenecks rather than a single catastrophic event. Proponents of the serial bottleneck hypothesis also point to the complex structure of human populations. Early humans did not exist as a single, well-mixed global population. They lived in small, isolated groups separated by vast distances and geographic barriers. This structure naturally limits gene flow and can create genetic patterns that resemble a bottleneck even without a catastrophic population crash. If populations were small and isolated for extended periods, genetic drift, the random fluctuation of gene frequencies in small populations, could have eliminated many genetic variants simply by chance, producing the low diversity we see today. The debate is further complicated by the imprecision inherent in both genetic and geological dating methods. While the molecular clock can tell us that a bottleneck occurred sometime between 50,000 and 100,000 years ago, pinpointing it to the exact moment of Toba at 74,000 years ago is challenging. The error bars on these estimates overlap with a wide window of time, during which multiple climatic and environmental stresses occurred. Similarly, dating the archaeological layers above and below the ash requires radiocarbon dating, which has its own uncertainties and limitations, especially at the outer edges of its effective range. This ongoing scientific controversy is not a weakness. It is a strength. It demonstrates that the scientific community is rigorously testing the Toba hypothesis, demanding high standards of evidence, and remaining open to alternative explanations. New technologies, from ancient DNA sequencing to high-resolution climate modeling, continue to shed light on this ancient mystery. And the truth, as always, will emerge from the careful accumulation and evaluation of evidence. One of the most compelling pieces of physical evidence for Toba's global impact is the volcanic ash layer itself, known to geologists as the youngest Toba tuff. This distinctive layer has been found in sediment cores from the South China Sea, the Indian Ocean, the Arabian Sea, and even as far as Lake Malawi in East Africa, over 7,000 kilometers from the eruption site. The ash has a unique geochemical fingerprint, allowing scientists to trace it definitively back to Toba. In India, ash deposits several meters thick blanket the landscape, preserving a snapshot of the catastrophe. Archaeological excavations reveal that stone tool technologies present before the ash layer are often missing or drastically reduced in complexity immediately after it, suggesting a disruption in human populations. This ash layer is a global marker, a frozen moment in time that divides the before and after of a planetary disaster. The youngest Toba tuff is unlike any other geological layer on Earth from the past 100,000 years. Its sheer extent and uniform characteristics make it an invaluable time marker, a horizontal line drawn across the planet that allows geologists and archaeologists to synchronize events that occurred thousands of kilometers apart. When researchers drill into the ocean floor or excavate terrestrial sites and encounter this distinctive gray layer, they know with certainty that they are looking at a deposit from a single event that occurred 74,000 years ago. The ash itself is composed primarily of volcanic glass. Tiny shards formed when molten rock was explosively fragmented and cooled almost instantly in the atmosphere. Under a microscope, these glass shards have characteristic shapes and textures, and their chemical composition, rich in silica and specific trace elements like zirconium and yttrium, is as unique as a fingerprint. Geochemists can analyze these trace elements using techniques like electron microprobe analysis or laser ablation mass spectrometry, measuring the concentrations of dozens of different elements with incredible precision. When they compare ash samples from widely separated locations, from a marine core in the Bay of Bengal to a lake sediment core in East Africa, the chemical signatures match perfectly. This is not just similar ash from similar eruptions. It is the same ash, dispersed across half the planet by stratospheric winds during the days and weeks following the eruption. The ability to identify and correlate this single layer across such vast distances is a testament to the eruption's extraordinary power and provides irrefutable evidence that Toba's impact was truly global. In India, the Toba ash layer is not a subtle feature that requires careful laboratory analysis to detect. It is a dramatic, landscape-altering deposit. In some regions, particularly in the central and southern parts of the subcontinent, the ash accumulated to depths of 3 to 6 meters, enough to bury small trees and completely transform the topography. Imagine walking across a landscape and encountering a cliff face or a road cut that exposes this ash layer, a thick band of uniform gray sediment sandwiched between darker soils. The sheer volume of ash represents an almost unimaginable quantity of pulverized rock, evidence of the violence of the eruption and the catastrophic impact it must have had on anything living in the region when it fell. The archaeological significance of the ash layer becomes clear when researchers excavate sites that span the Toba event. At several locations in India, stone tools have been found both below and above the ash. In some cases, as the skeptics point out, the tools show continuity, suggesting persistent occupation. But in other cases, the evidence tells a different story. At certain sites, the density of tools drops dramatically above the ash, and the types of tools change, becoming simpler or showing different manufacturing techniques. This could indicate a population crash, followed by either recovery by a diminished group or recolonization by a different population. The layer also sometimes contains evidence of burning and vegetation change, preserved as charcoal and altered pollen profiles, showing that the ashfall was accompanied by ecological disruption. In marine sediment cores, the Toba ash layer appears as a thin but distinct band, often just a few centimeters thick, representing the ash that settled through the water column to the ocean floor. The fact that it can be detected at all in these deep-sea environments, far from the eruption source, is remarkable. The ash would have been carried aloft to extreme altitudes, remained suspended for days or weeks, and then slowly settled out, blanketing the ocean surface over vast areas. Studies of these marine cores allow scientists to reconstruct the dispersal pattern of the ash cloud and estimate how long it remained airborne, providing crucial data for climate models that simulate the volcanic winter. Perhaps most importantly, the ash layer serves as a precise chronological anchor. By dating the ash using radiometric techniques, particularly argon-argon dating of the volcanic minerals it contains, scientists have pinpointed the eruption to 73,180 years ago, plus or minus a few hundred years. This date can then be used to calibrate other dating methods and to correlate events across different regions and different types of evidence. The youngest Toba tuff is more than just evidence of a volcanic eruption. It is a global timestamp, a physical record of a planetary catastrophe that allows us to ask and answer questions about what happened to life, to ecosystems, and to humanity at that precise moment in Earth's history. Modern climate scientists use sophisticated computer models to simulate the effects of a Toba-scale eruption on global weather patterns. These models incorporate volcanic aerosol dispersal, atmospheric chemistry, ocean currents, and feedback loops between ice, land, and sea. The results are sobering. Most models predict a rapid drop in surface temperatures, a reduction in monsoon rainfall, and a weakening of the hydrological cycle, meaning less evaporation and precipitation globally. Some simulations suggest that the volcanic winter could have triggered a positive feedback loop, causing ice sheets to expand and further cooling the planet, potentially tipping the Earth into a prolonged cold phase. These models align with evidence from ice cores in Greenland and Antarctica, which shows sulfate spikes and temperature anomalies corresponding to the Toba eruption timeframe. The science paints a picture of a planet thrust into chaos, with catastrophic consequences for all life, especially for a vulnerable species like early humans. Climate modeling has become one of the most powerful tools in Earth science, allowing researchers to conduct experiments that would be impossible in the real world. By encoding the fundamental laws of physics and chemistry into massive computer programs and feeding them data about the atmosphere, oceans, land surface, and ice sheets, scientists can simulate how the climate system responds to different perturbations. In the case of Toba, researchers input the estimated volume of ash and sulfur dioxide ejected by the eruption, specify the altitude to which it was injected, and then let the model run, calculating how these materials would disperse around the globe and what effects they would have on temperature, precipitation, and atmospheric circulation. The models reveal a cascade of interconnected effects. The initial injection of sulfur dioxide into the stratosphere leads to the formation of sulfuric acid aerosols within weeks. These aerosols, suspended in the stratosphere where there is no rain to wash them out, form a reflective layer that encircles the planet. The models calculate how much incoming solar radiation this layer would reflect back to space, and the answer is startling. Depending on the model and the assumptions made about the eruption's characteristics, the reduction in solar energy reaching the surface ranges from 10% to 25%. This may not sound dramatic, but when applied globally and sustained for years, it is enough to plunge the planet into a deep freeze. Surface temperatures in the models drop by an average of 3 to 5 degrees Celsius globally, with much larger drops in continental interiors and high latitudes, potentially reaching 10 to 15 degrees in some regions. The cooling affects more than just temperature. The hydrological cycle, the continuous movement of water between the ocean, atmosphere, and land through evaporation, precipitation, and runoff, weakens dramatically. Cooler temperatures mean less evaporation from the oceans. Less evaporation means less moisture in the atmosphere. Less atmospheric moisture means less precipitation. The models show that monsoon systems, which billions of organisms depend on for seasonal rains, would have been particularly hard hit. The African and Asian monsoons, driven by temperature differences between land and ocean, would have weakened or even failed entirely for several years. For humans and other species that timed their migrations and reproductive cycles to these seasonal rains, the disruption would have been catastrophic. Some of the most concerning results from the models involve feedback loops, processes where an initial change triggers secondary changes that amplify the original effect. The ice albedo feedback is particularly dangerous. As temperatures drop, snow and ice cover expand. Snow and ice are highly reflective, bouncing even more solar radiation back to space, which causes further cooling, which causes more snow and ice to form, and so on. Some Toba simulations suggest that this feedback could have been triggered, causing ice sheets that were already extensive during the Ice Age to expand even further and persist longer. This would have turned a temporary volcanic winter lasting a few years into a prolonged cold period lasting decades or even centuries, essentially extending the Ice Age and delaying the next warming phase. The ice core evidence provides crucial validation for these models. Ice cores drilled from the Greenland and Antarctic ice sheets are annual records of past climate, with each year's snowfall preserved as a distinct layer. Scientists can count these layers like tree rings to establish a chronology, and they can analyze the chemical composition of the ice to reconstruct past temperatures and atmospheric conditions. At a depth corresponding to approximately 74,000 years ago, multiple ice cores show a sharp spike in sulfate concentration, the chemical signature of volcanic aerosols settling out of the atmosphere. This spike is one of the largest in the entire ice core record, confirming that Toba's atmospheric impact reached even the polar regions. Immediately following the sulfate spike, some cores show temperature proxies indicating cooling, though the magnitude and duration are debated and vary between cores. The models also simulate the ecological consequences of the climate changes. They incorporate vegetation models that predict how different plant types respond to temperature and precipitation changes. The results show widespread die-off of forests and grasslands, contraction of habitable zones toward the equator, and expansion of desert and tundra regions. When these vegetation changes are coupled with animal population models, the simulations predict mass extinctions of large mammals and severe population crashes for omnivores like humans. While these ecological models are less certain than the physical climate models, they provide a framework for understanding how the climate disruption would have propagated through the food web, ultimately affecting every species on the planet. The humans who survived the Toba catastrophe were not simply lucky. They possessed a critical advantage, a flexible and innovative toolkit, both literal and cognitive. Archaeological evidence from this period shows that humans were capable of crafting a variety of specialized stone tools, including blades, scrapers, and projectile points. These tools allowed them to hunt, butcher, and process plant materials and create clothing and shelter. But more importantly, they had fire. The ability to control fire provided warmth in the sudden cold, a means to cook otherwise inedible or toxic plants to extract nutrients, and a social focal point that strengthened group cohesion. Fire was the ultimate survival technology. Combined with complex social structures, language, and the ability to plan and share knowledge, these traits allowed the survivors to adapt to rapidly changing and hostile environments in ways no other species could. The stone tools crafted by early humans 74,000 years ago were products of thousands of generations of accumulated knowledge. Each tool type represented a specific solution to a specific problem, refined over millennia through trial and error. Hand axes, with their symmetrical teardrop shape and sharp edges, were versatile cutting and chopping implements that could butcher large animals, process plant materials, and even dig for roots and tubers. Scrapers, with their carefully shaped working edges, were essential for processing animal hides, removing fat and tissue to create leather for clothing, bags, and shelter coverings. In the sudden cold of the volcanic winter, the ability to create insulated clothing from animal skins would have been the difference between survival and death from exposure. Projectile points, hafted onto wooden spears or thrown as darts, extended the human reach and allowed hunters to take down game from a safer distance, reducing the risk of injury. But the physical toolkit was only part of the story. The cognitive toolkit, the mental capabilities and cultural knowledge that humans possessed, was equally important. Language, the ability to communicate complex ideas through symbolic sounds, allowed groups to coordinate hunting strategies, share information about distant resources, warn each other of dangers, and transmit knowledge from elders to the young. A woman who had learned from her mother which plants were safe to eat during times of scarcity could pass that knowledge to her daughters, creating an intergenerational chain of survival information. A hunter who discovered a new water source or a sheltered valley with game could describe its location to others, multiplying the benefit of his discovery across the entire group. Fire was perhaps the single most important technology in the survivors' arsenal. Humans had controlled fire for hundreds of thousands of years by the time Toba erupted, and this ancient partnership with combustion proved essential during the volcanic winter. Fire provided heat, allowing humans to survive in temperatures that would otherwise have been lethal. It provided light, extending the productive hours of the day into the night and offering psychological comfort in the darkness. Fire transformed inedible foods into edible ones. Many plant materials contain toxins that can cause illness or death if consumed raw, but heating breaks down these compounds, rendering the plants safe and nutritious. Roots, tubers, and certain seeds that would have been rejected by other animals became viable food sources for humans with fire. Fire could also be used to crack open bones to extract the calorie-rich marrow inside and to render fat for storage and later consumption. The social dimension of fire cannot be overstated. A fire in the center of a camp became a gathering place, a hearth around which the group assembled for warmth, food preparation, and social interaction. Stories were told around these fires. Knowledge was shared, social bonds were reinforced, and group identity was strengthened. In times of extreme stress, when resources were scarce and survival was uncertain, the cohesion of the group became critical. A united group that shared resources, supported its weaker members, and worked together was far more likely to survive than individuals or fragmented groups competing against each other. Fire facilitated this cohesion, creating a physical and social center that held communities together. The survivors also possessed the cognitive ability to plan for the future and adapt their strategies based on changing conditions. This capacity for forward thinking and behavioral flexibility distinguished humans from other species. When traditional food sources disappeared, humans could innovate, experimenting with new foods, new hunting techniques, and new tools. When familiar territories became uninhabitable, they could migrate to new regions, assess the resources available, and develop strategies to exploit them. This adaptability was not just individual, but cultural. Groups that developed successful survival strategies could teach them to others, creating a collective intelligence that was greater than the sum of its parts. The survivors of Toba were also likely highly selective in their risk-taking. In normal times, humans might have been exploratory, trying new foods or venturing into unfamiliar territories. But during the crisis, the margin for error was zero. Every decision had to be calculated. The survivors would have relied heavily on proven knowledge, sticking to foods and strategies they knew worked, avoiding unnecessary risks. They would have been conservative in their movements, staying near known water sources and productive areas rather than wandering into unknown regions. This combination of innovation when necessary and conservatism when prudent was the hallmark of human survival during the bottleneck. Some researchers propose that the Toba bottleneck did more than just reduce human numbers. It fundamentally changed us. The intense selective pressure of the volcanic winter may have acted as an evolutionary crucible, favoring individuals with enhanced cognitive abilities, creativity, problem-solving skills, and social cooperation. Those who could innovate, who could imagine new solutions to unprecedented problems, who could communicate complex plans and work together cohesively, were the ones who survived and passed on their genes. This idea is linked to the concept of the cognitive revolution, a hypothetical leap in human mental capacity that occurred sometime between 70,000 and 50,000 years ago. After this point, the archaeological record shows an explosion of symbolic behavior. Art, jewelry, musical instruments, sophisticated weapons, and complex burial rituals. It is as if a switch was flipped, and modern human behavior, as we recognize it, suddenly emerged from the ashes of Toba. The cognitive revolution theory suggests that the crisis created by Toba acted as a filter, sorting humans based on their mental capabilities in a way that normal environmental conditions never could. In ordinary times, a wide range of cognitive abilities might be sufficient for survival. A person who was good at tracking animals but poor at social interaction could still survive by specializing in solitary hunting. A person who excelled at remembering plant locations but struggled with innovation could thrive by sticking to traditional food sources. But when the volcanic winter struck and every traditional strategy failed, only those individuals who could think flexibly, who could imagine alternatives, who could learn rapidly and share that learning with others, would have had a chance. The crisis eliminated everyone who was merely adequate and preserved only those who were exceptional. This selective process would have operated at multiple levels. At the individual level, people with better problem-solving abilities would have been more successful at finding food, creating shelter, and avoiding dangers. They would have been more likely to survive long enough to reproduce. At the group level, bands that fostered cooperation, that had mechanisms for sharing resources and knowledge, that could resolve conflicts without splintering, would have out-survived groups that were more fractious or hierarchical. The genes of the cooperative, innovative individuals and the cultural practices of cohesive groups would have been disproportionately represented in the post-Toba population. Over just a few generations, this could have shifted the average cognitive and behavioral traits of the human species. What evidence supports this theory? The archaeological record provides tantalizing clues. Before roughly 70,000 years ago, human material culture was relatively uniform and conservative. Stone tools changed slowly over thousands of years. There is little evidence of personal ornamentation, symbolic art, or complex ritual behavior. Humans were capable, certainly, but their creativity seemed constrained. Then, sometime after Toba, something changed. The Middle Stone Age in Africa, which immediately follows the Toba time frame, shows the first widespread evidence of symbolic behavior. At Blombos Cave in South Africa, archaeologists have found engraved ochre pieces and shell beads dating to around 75,000 years ago, right at the cusp of the Toba event. These are not functional objects. They are symbols, carriers of meaning, evidence of minds that were thinking abstractly, that valued beauty and identity. Shortly thereafter, the archaeological record explodes with innovation. By 50,000 years ago, humans were creating sophisticated composite tools, weapons made from multiple materials carefully joined together, like spear throwers that increased the range and force of projectiles. They were making bone needles, indicating the production of fitted, sewn clothing, a technology that would have been essential for surviving in colder climates. They were creating art, not just simple marks, but complex geometric patterns, and eventually, by 40,000 years ago, the stunning cave paintings of Europe and the carved figurines that speak to a fully developed symbolic imagination. They were burying their dead with grave goods, flowers, and ochre, suggesting beliefs about an afterlife or the importance of honoring the deceased. These behaviors are the hallmarks of modern human cognition, and their sudden appearance in the archaeological record after Toba is striking. Language likely played a central role in this cognitive transformation. While humans almost certainly had some form of language before Toba, the crisis may have selected for more sophisticated linguistic abilities. The ability to discuss hypothetical scenarios, to plan for future events, to describe abstract concepts, would have been invaluable during a time when traditional knowledge was insufficient. A group that could say, if we travel 3 days east, we might find the valley where the herds used to gather before the cold came. And debate the merits of that plan would have a significant advantage over a group limited to communicating about the immediate present. The genetic evidence hints at this as well. The FAXP2 gene, which is essential for the fine motor control required for speech, shows signs of having been under strong selective pressure in recent human evolution, though pinpointing exactly when is difficult. The Toba bottleneck may also have fostered social and emotional intelligence. In a world where resources were desperately scarce, the ability to read the intentions and emotions of others, to build alliances, to negotiate and cooperate, would have been critical. Individuals who were socially adept, who could build trust and reciprocal relationships, would have been better positioned to access shared resources and receive help in times of need. The capacity for empathy, for understanding another's suffering and offering assistance, might have been actively selected for during this period. The survivors were not just the smartest or the strongest. They were the most human, the ones who could connect, communicate, and care for each other in the face of unimaginable hardship. Shortly after the proposed Toba bottleneck, the archaeological record begins to fill with evidence of symbolic thought and artistic expression. In South Africa, the Blombos cave contains ochre engravings and shell beads dating to around 75,000 years ago, right on the cusp of the Toba event. These are not utilitarian objects. They are deliberate creations meant to convey meaning, identity, or beauty. Ochre, a red pigment, appears in archaeological sites across Africa, suggesting it was valued and traded. This marks the dawn of art, the first evidence that humans were not just surviving, but creating, imagining, and communicating abstract ideas. The survivors of Toba were not just a remnant population. They were the bearers of a new kind of consciousness, one that would eventually allow them to reshape the world in their image, to tell stories, to dream, and to remember. The ochre engravings discovered at Blombos Cave are geometric patterns, cross-hatched lines carefully incised into pieces of ochre stone. To modern eyes, they might seem simple, even crude, but their significance cannot be overstated. These marks represent a fundamental shift in human cognition. Someone, 75,000 years ago, sat down with a piece of ochre and a sharp stone tool and deliberately created a pattern that had no functional purpose. It was not a tool. It was not food. It was an idea made visible, a thought externalized into the physical world. This is the essence of symbolic behavior, the ability to let one thing stand for another, to create representations of concepts that exist only in the mind. The person who created these engravings was demonstrating that they could think abstractly, that their mind was not limited to the immediate, concrete world of survival, but could wander into the realm of meaning and expression. The shell beads found alongside the ochre are equally significant. These are tiny marine snail shells, each carefully perforated to allow them to be strung together, likely as a necklace or bracelet. The holes were made by deliberately striking the shells or grinding them, a process that required time, patience, and skill. The shells themselves were not local to the cave. They had to be collected from the coast, which meant someone valued them enough to carry them inland, or there was a trade network that moved these objects between groups. Why would anyone bother with such seemingly frivolous items during a time of potential crisis? The answer is that these beads were not frivolous. They were powerful. They served as markers of identity, symbols that communicated who you were, which group you belonged to, your status within that group, perhaps even your personal achievements or spiritual beliefs. Ochre, the red pigment that appears with increasing frequency in archaeological sites after Toba, is another window into the emerging symbolic mind. Ochre is iron oxide, a naturally occurring mineral that can range in color from yellow to deep red depending on its composition. It has no nutritional value and limited practical use, yet humans collected it, ground it into powder, mixed it with fat or water to create paint, and applied it to their bodies, their tools, their living spaces, and eventually, their dead. The effort invested in obtaining and processing ochre suggests it held profound significance. Some researchers believe it was used in rituals, perhaps to mark important life transitions like birth, puberty, or death. Others suggest it served as a kind of social glue, a shared symbolic system that helped bind groups together and distinguish them from outsiders. The appearance of these symbolic behaviors immediately after the Toba time frame is unlikely to be coincidental. The catastrophe may have created conditions that made symbolic communication not just advantageous, but necessary. When the world becomes unpredictable and traditional knowledge fails, symbols become tools for creating shared meaning and maintaining group cohesion. A shell bead necklace becomes a sign of alliance, a mark that says, "I belong to this group and we help each other." An ochre pattern becomes a ritual object that invokes protection or success in a hunt. A carved line on a stone becomes a record, a way to mark time or remember an event. In a world stripped of its familiar landmarks and rhythms by the volcanic winter, these symbols may have provided psychological and social anchors, ways to maintain identity and purpose in the face of chaos. The artistic impulse that emerged during this period was not limited to portable objects. Evidence suggests that humans also began to modify their environments in symbolic ways. At several African sites, archaeologists have found evidence of structured living spaces, arrangements of stones or post holes that indicate deliberate construction of shelters with defined areas for different activities. This is not just building for function. It is building with intent, creating spaces that reflect an understanding of order and purpose. The hearth is placed in the center, sleeping areas are arranged around it. Tool-making debris is confined to one area, food processing to another. This is architecture in its earliest form, the imposition of human design onto the natural world. The people who created these first artworks were our direct ancestors, the survivors of Toba and their immediate descendants. They were living in a world still recovering from catastrophe, still marked by scarcity and uncertainty. Yet they found the time and energy to create beauty, to express themselves, to communicate through symbols. This tells us something profound about human nature. Even in our darkest moments, perhaps especially in our darkest moments, we create. We seek meaning. We connect with each other through shared symbols and stories. The first artists were not just decorating their world. They were inventing culture, laying the foundation for every piece of art, every story, every song that would follow. They were proving that humanity is more than survival. It is imagination, expression, and the relentless drive to make meaning from chaos. With the volcanic winter finally subsiding and climate slowly stabilizing, the descendants of the Toba survivors began to expand outward from their African refuge. Genetic evidence suggests a major out-of-Africa migration event occurred approximately 60,000 to 70,000 years ago. Small groups of humans, perhaps numbering only a few hundred individuals, crossed the Bab el-Mandeb Strait at the southern end of the Red Sea, entering the Arabian Peninsula. From there, they spread rapidly along coastal routes, following the shorelines of the Indian Ocean, reaching South Asia, Southeast Asia, and eventually Australia by around 50,000 years ago. This was not a slow diffusion, but a relatively rapid expansion enabled by their enhanced cognitive abilities, cooperative social structures, and adaptable technologies. These migrating groups carried with them the genetic legacy of the bottleneck, a homogeneity that would spread across the globe, making every human population a distant cousin. The Great Migration out of Africa was one of the most consequential events in human history. It transformed Homo sapiens from an African species into a global one, setting in motion the colonization of every habitable continent and the eventual dominance of our species over all others. But this expansion was not a planned conquest or deliberate exploration. It was likely a gradual, almost accidental process driven by population pressure, curiosity, and the endless human search for resources. As the climate recovered from the Toba catastrophe and populations slowly rebuilt, groups at the edges of the inhabited range would have naturally expanded into adjacent territories. Over generations, this incremental movement carried humans further and further from their ancestral homeland. The root of the first successful migration is written in our genes. By analyzing the distribution of genetic variants across modern populations, researchers have reconstructed the path our ancestors took. The genetic data points to a relatively small founding group, perhaps just a few hundred individuals, who left Africa sometime between 60,000 and 70,000 years ago. They crossed the Bab el-Mandeb Strait, the narrow waterway separating the Horn of Africa from the Arabian Peninsula. During periods of low sea level, this strait would have been even narrower, perhaps only a few kilometers wide, making the crossing feasible using simple rafts or even by island hopping during low tide. This was humanity's gateway to the rest of the world. Once in Arabia, the migrants found a landscape very different from today's barren deserts. During wetter periods of the Ice Age, the Arabian Peninsula was covered with grasslands, lakes, and river systems, supporting abundant wildlife. Archaeological evidence shows that humans exploited these resources, leaving behind stone tools and campsites. But the Arabian environment was unstable, prone to rapid shifts between wet and dry periods. This may have driven the migrants to keep moving, following the coasts and river valleys that provided reliable water and food. The coastal route hypothesis suggests that early humans hugged the shorelines of the Indian Ocean, exploiting rich marine resources like shellfish, fish, and seabirds. Coastal environments are highly productive and relatively predictable, making them ideal corridors for migration. The speed of the expansion is remarkable. Genetic and archaeological evidence suggests that humans reached South Asia within a few thousand years of leaving Africa, Southeast Asia shortly thereafter, and Australia by around 50,000 years ago. To reach Australia required crossing significant stretches of open ocean, even when sea levels were lower. This means that by this time, humans had developed seafaring capabilities, building boats sturdy enough to carry groups of people, their tools, and supplies across dozens of kilometers of water. The cognitive and technological leap this represents is staggering. Navigation, boat construction, and the social organization required to plan and execute such a journey all point to a species that had fully entered the modern cognitive realm. The migrants carried with them more than just their genes. They carried their culture, their knowledge, their languages, and their symbolic systems. Each group that split off from the main migrating wave and settled in a new region became the founding population for that area. And over time, they would develop distinct cultural identities, adapted to their local environments. But beneath these surface differences, they all shared the deep genetic signature of the bottleneck, the mark of their common origin in post-Toba Africa. This is why genetic studies consistently show that non-African populations have even less genetic diversity than African populations. They all descend from the subset of survivors who left Africa, carrying only a portion of the already reduced genetic variation that existed on the continent. As humans spread across Asia, they encountered environments vastly different from the African savannas and woodlands they had evolved in. Tropical rainforests, temperate forests, arid steppes, high mountains, each presented unique challenges and required adaptations. But the cognitive revolution that had been forged in the fires of Toba gave them the mental tools to adapt. They learned to hunt new prey animals, to identify and process new plant foods, to create new types of clothing and shelter suited to different climates. They were no longer a species tied to a single environment. They were a species that could learn to live anywhere. The migration was not a single wave, but a complex, branching process. Some groups moved rapidly along the coasts. Others moved inland, following river valleys into the heart of Asia. Some groups stopped and settled in favorable locations, building stable populations. Others kept moving, driven by wanderlust or pushed by competition. Over thousands of years, this process filled Asia with human populations, each adapting to their local conditions, but all connected by their shared ancestry, their shared genetic legacy, and ultimately, their shared origin in a small group of survivors who had endured the worst that nature could throw at them and emerged ready to conquer the world. As Homo sapiens spread out of Africa, they were not entering an empty world. Other human species had preceded them. Neanderthals dominated Europe and parts of Western Asia. Denisovans, a mysterious sister species known mainly from genetic evidence and a few fossils, lived in Asia. Homo erectus populations may have still persisted in isolated pockets. These encounters between different human species were complex, involving competition, cooperation, and interbreeding. Genetic studies reveal that non-African modern humans carry small percentages of Neanderthal DNA. Evidence of interbreeding that occurred around 50,000 to 60,000 years ago. Some populations also carry Denisovan DNA, particularly in Melanesia and Australia. These genetic ghosts are remnants of our extinct cousins, absorbed into the expanding wave of Homo sapiens. But ultimately, only one human species would survive to the present day, and the Toba survivors, with their cognitive edge, may have been key to that outcome. The Neanderthals were formidable beings, powerfully built and adapted to the harsh climates of Ice Age Europe and Western Asia. They had large brains, comparable in size to our own, and were sophisticated toolmakers who controlled fire, hunted large game, and cared for their sick and elderly. They had been successfully living in Eurasia for hundreds of thousands of years before Homo sapiens arrived. Archaeological evidence shows they buried their dead, created symbolic objects, and even wore body decorations. In many ways, they were remarkably similar to us. Yet when modern humans began expanding into their territories around 50,000 years ago, the Neanderthals were already a declining species, with small, fragmented populations scattered across their range. Within 10,000 years of our arrival, they were extinct. What happened when these two human species met? The archaeological record provides frustratingly few direct answers. We find sites where Neanderthal tools and Homo sapiens tools appear in nearby layers, suggesting they occupied the same regions at different times. But rarely do we find evidence of direct interaction. Were the encounters violent, marked by conflict and competition for resources? Or were they peaceful, characterized by trade, cultural exchange, and perhaps even cooperation? The truth was likely both, varying from place to place and time to time. Some groups may have coexisted peacefully, even forming alliances. Others may have been rivals, competing for the same hunting grounds and resources, leading to conflict and displacement. The genetic evidence, however, tells a clear and surprising story. Modern humans did not simply replace Neanderthals. We interbred with them. When scientists first sequenced the Neanderthal genome in 2010, they discovered that non-African modern humans carry approximately 1% to 2% Neanderthal DNA. This means that sometime between 50,000 and 60,000 years ago, as Homo sapiens moved into the Middle East and Europe, some individuals from the two species mated and produced fertile offspring. These hybrid children survived, reproduced, and their descendants carried Neanderthal genes forward into the modern human population. Today, billions of people carry fragments of Neanderthal DNA in their genomes, genetic echoes of encounters that took place tens of thousands of years ago. The Denisovans are even more mysterious. Known primarily from a handful of bone fragments and teeth found in Denisova Cave in Siberia, they are a sister species to Neanderthals, sharing a common ancestor but diverging hundreds of thousands of years ago. We know very little about what they looked like or how they lived, but their genetic legacy is preserved in modern populations. People of Melanesian and Australian descent carry significant amounts of Denisovan DNA, up to 5% in some cases, indicating that Homo sapiens encountered and interbred with Denisovans as they migrated through Southeast Asia and into Oceania. Some Denisovan genetic variants have been positively selected in modern populations, meaning they provided adaptive advantages. For example, a Denisovan gene variant related to high-altitude adaptation is common in Tibetan populations today, helping them survive in low-oxygen environments. The interbreeding between species raises profound questions about identity and boundaries. If Homo sapiens and Neanderthals could produce fertile offspring, were they truly separate species? Modern definitions of species often rely on reproductive isolation, the idea that members of different species cannot interbreed or produce fertile offspring. But the human story is more complicated. We were separate enough to have evolved distinct physical characteristics and cultural traditions, yet similar enough to produce viable hybrids. This suggests that the boundaries between human species were porous, not rigid walls, but permeable membranes that allowed genetic and cultural exchange. Yet despite this interbreeding, only Homo sapiens survived. The Neanderthals vanished around 40,000 years ago. The Denisovans disappeared from the fossil record at roughly the same time. Homo erectus, if any populations persisted into this period, also went extinct. Why did we survive when they did not? The answer likely lies in the combination of factors that made Homo sapiens unique. Our cognitive abilities, sharpened by the Toba crisis, gave us an edge in innovation and adaptability. Our social structures, perhaps more complex and cooperative, allowed us to form larger networks and support bigger populations. Our language, potentially more sophisticated, enabled better coordination and knowledge transmission. We may have simply outcompeted the other species, not through violence, but through superior efficiency in exploiting resources, faster population growth, and greater resilience to environmental change. It is also possible that the interbreeding itself contributed to the extinction of Neanderthals and Denisovans. If hybrid individuals were absorbed into Homo sapiens populations, the smaller populations of the other species would have lost reproductive potential, accelerating their decline. In the end, all that remains of our extinct cousins are the ghost genes they left behind in our genomes, fragments of their existence, woven into ours, a testament to encounters in the deep past when multiple human species walked the earth together for the last time. By 45,000 years ago, Homo sapiens had penetrated deep into the Eurasian continent. They moved into the Levant, the crossroads between Africa and Asia, and from there into Europe, gradually displacing Neanderthal populations. In the harsh, Ice Age climates of glacial Europe, these humans demonstrated remarkable adaptability. They developed tailored clothing from animal skins, built sophisticated shelters from mammoth bones and hides, and crafted an array of specialized tools for hunting large game. Cave paintings in sites like Chauvet and Lascaux in France, dating to 30,000 years ago, showcase their artistic prowess and deep connection to the animals they hunted. These were not primitive savages eking out a bare existence. They were skilled, resourceful people with rich cultural lives. Their expansion across Eurasia was a testament to the evolutionary advantages forged in the crucible of the Toba catastrophe. The colonization of Europe was perhaps the most challenging expansion Homo sapiens had undertaken. These were not the warm, familiar landscapes of Africa or the coastal routes of southern Asia. This was Ice Age Europe, a vast, frozen wilderness where temperatures regularly plunged below freezing, where winters lasted months, and where survival required not just intelligence, but ingenuity and extraordinary endurance. Glaciers covered Scandinavia and the Alps, extending fingers of ice deep into the continent. Between these frozen barriers lay open steppes and tundra, cold grasslands swept by fierce winds and populated by massive herds of woolly mammoths, bison, reindeer, and horses. To thrive here, humans had to reinvent themselves. Clothing became a matter of life and death. The simple animal skins that might have sufficed in warmer climates were inadequate against the European cold. Archaeological evidence, including bone needles with eyes for thread, indicates that humans developed tailored, fitted clothing around this time. They were sewing garments from multiple pieces of hide, creating insulated layers that trapped body heat. They likely wore leather boots stuffed with grass for insulation, hooded parkas made from fur, and mittens to protect their hands. This was sophisticated textile technology, requiring knowledge of how to tan and soften hides, how to cut patterns, and how to create durable stitching using sinew or plant fibers. Without these innovations, the European winter would have been deadly. Shelter construction also reached new levels of complexity. In regions where wood was scarce, humans turned to an unlikely building material, mammoth bones. At sites across the Ukrainian and Russian steppes, archaeologists have uncovered the remains of dwellings constructed from hundreds of mammoth bones and tusks, arranged in circular patterns and likely covered with hides to create wind-resistant, insulated structures. These were not temporary camps, but substantial long-term dwellings that required planning, cooperation, and considerable labor to build. The fact that humans invested such effort in construction indicates they were establishing semi-permanent settlements, staying in one location long enough to make it worth building substantial shelters. The hunting technologies developed during this period were revolutionary. Humans created the atlatl, or spear thrower, a lever device that dramatically increased the force and range with which a spear could be thrown, allowing hunters to bring down dangerous game from a safer distance. They crafted sophisticated projectile points from stone and bone designed for maximum penetration and damage. They developed strategies for cooperative hunting, driving entire herds of animals toward cliffs or into constructed traps where they could be killed en masse. Evidence from kill sites shows that humans were not just opportunistic scavengers or individual hunters. They were organized, strategic predators capable of taking down the largest and most dangerous animals on the continent. The artistic explosion that occurred in Ice Age Europe is one of the most awe-inspiring aspects of this colonization. The cave paintings discovered at Chauvet, Lascaux, Altamira, and dozens of other sites represent a sophistication of artistic expression that rivals anything produced in later human history. These are not crude stick figures, but masterful, dynamic representations of animals, horses galloping, bison charging, lions prowling, rendered with anatomical accuracy and artistic flair that speaks to deep observation and skilled hands. The artists used multiple colors, created shading and perspective, and placed their images in ways that utilize the natural contours of the cave walls to create three-dimensional effects. These paintings were created deep inside dark caves, far from the entrances, requiring the use of lamps or torches and representing significant investment of time and resources. What were these paintings for? We can only speculate, but they were clearly not simple decoration. They may have been part of shamanic rituals, spiritual journeys into the underworld of the cave, to commune with animal spirits and ensure hunting success. They may have been teaching tools, ways to transmit knowledge about animal behavior to younger generations. They may have been expressions of identity, markers of territory, or clan affiliation. Whatever their specific purpose, they demonstrate that the humans who created them had rich inner lives, complex belief systems, and the capacity for abstract thought and symbolic expression that defines modern human consciousness. The colonization of Eurasia was complete by around 40,000 years ago, with Homo sapiens populations established from the Atlantic coast to the Pacific, from the Mediterranean to the Arctic Circle. These were the descendants of the Toba survivors, carrying their genetic legacy across the world, adapting to every environment they encountered, and leaving behind a trail of innovation, art, and cultural complexity that announced the arrival of a new dominant species on Earth. The human colonization of the Americas represents the final chapter in our species' global expansion. During the last ice age, sea levels were significantly lower, exposing a land bridge known as Beringia between Siberia and Alaska. Genetic and archaeological evidence suggests that small groups of humans crossed this bridge approximately 15,000 hours to 20,000 years ago, though some evidence hints at earlier arrivals. These pioneering groups moved southward through ice-free corridors or along coastal routes, rapidly spreading from the Arctic to the southern tip of South America within a few thousand years. They encountered and hunted now extinct megafauna like mammoths, giant ground sloths, and saber-toothed cats. The Native American populations that emerged from these founding groups carry the same genetic signature of the African bottleneck, a testament to the single origin of all modern humans and the long journey from a tiny tribe in Africa to every corner of the earth. Beringia was not a narrow bridge, but a vast subcontinent, a cold grassland steppe that at its maximum extent stretched over 1,600 kilometers from north to south, connecting the landmasses of Asia and North America. This was a harsh but productive environment, supporting populations of large herbivores and the predators that hunted them. Humans living in northeastern Siberia, already adapted to extreme Arctic conditions, would have naturally expanded their hunting territories eastward into Beringia, following the herds. Over generations, this gradual movement carried them across what is now the Bering Strait without them even realizing they were entering a new continent. They were simply following the animals, seeking resources, living their lives as their ancestors had for thousands of years. The exact timing and route of entry into the Americas has been hotly debated for decades. The traditional model proposed that humans waited in Beringia until the massive ice sheets covering Canada, the Laurentide and Cordilleran glaciers, retreated enough to open an ice-free corridor running along the eastern slopes of the Rocky Mountains. Once this corridor opened, around 14,000 years ago, humans poured southward into the rich, game-filled landscapes of the continental interior. This model aligned well with the Clovis culture, named after distinctive projectile points first discovered near Clovis, New Mexico, which appeared across North America around 13,000 years ago and represented the earliest widespread archaeological evidence of human presence. However, this neat narrative has been challenged by mounting evidence of pre-Clovis occupation. Archaeological sites in both North and South America have yielded dates older than the supposed opening of the ice-free corridor. Monte Verde in southern Chile, one of the most thoroughly documented pre-Clovis sites, contains artifacts and structural remains dating to at least 14,500 years ago, and possibly much earlier. If humans were in southern South America by this time, they must have entered the Americas earlier and traveled thousands of kilometers southward before the ice-free corridor even opened. This has led researchers to propose an alternative route, a coastal migration along the Pacific Rim, where people traveled by boat, hugging the coastline from Beringia down through Alaska, British Columbia, and eventually all the way to South America. Rising sea levels since the Ice Age have drowned this ancient coastline under hundreds of feet of water, making archaeological evidence difficult to find. But the genetic and chronological data increasingly support this coastal route hypothesis. The speed of the expansion once humans entered the Americas is breathtaking. Within perhaps 2,000 years, humans had spread from Alaska to Tierra del Fuego at the southern tip of South America, a distance of over 15,000 kilometers. This represents one of the fastest large-scale migrations in human history. The Americas were a pristine landscape, untouched by human hands, teeming with wildlife that had never encountered human hunters. The megafauna, massive animals like Columbian mammoths standing 4 meters tall, giant ground sloths the size of elephants, saber-toothed cats, dire wolves, and massive short-faced bears had no fear of these small, bipedal newcomers. This naivety made them easy prey for skilled human hunters armed with sophisticated weapons and cooperative hunting strategies. The arrival of humans coincided with the most dramatic wave of extinctions the Americas had experienced in millions of years. Within a few thousand years of human arrival, approximately 80% of large mammal species in North America went extinct. In South America, the toll was similar. 34 genera of large mammals disappeared, including all of the continent's giant ground sloths, its native horses and camels, and its unique megafauna, like the car-sized armadillo-like glyptodonts. While climate change at the end of the Ice Age played a role in stressing these populations, the correlation between human arrival and extinction is striking and difficult to dismiss. Humans were likely the decisive factor, hunting these animals faster than they could reproduce and fundamentally altering the ecology of 2 continents. The Native American populations that arose from these founding groups developed extraordinary diversity in their cultures, languages, and adaptations. From the Arctic hunters who pursued seals and whales in the frozen north, to the complex agricultural civilizations that arose in Mesoamerica and the Andes, to the sophisticated hunter-gatherers of the Pacific Northwest and the Amazon rainforest. Each group adapted brilliantly to their local environment. Yet genetically, they all trace back to a small founding population that crossed from Asia, and ultimately, like all humans everywhere, they trace back to the survivors of Toba. The Americas were the final frontier, the last major landmasses to be colonized by our species. With their settlement, Homo sapiens had completed a journey that began in the heart of Africa 200,000 years earlier, survived a near-extinction event 74,000 years ago, and culminated in a global presence that no other large mammal in Earth's history had ever achieved. Wherever modern humans arrived, a wave of extinctions often followed. In Australia, megafauna like the giant kangaroo Procoptodon and the marsupial lion Thylacoleo disappeared within a few thousand years of human arrival. In the Americas, the arrival of humans coincided with the extinction of over 80% of large mammal species. In Eurasia, mammoths, woolly rhinoceroses, and cave bears vanished. While climate change played a role, many scientists believe human hunting pressure was the decisive factor. Armed with advanced weapons, strategic hunting techniques, and the ability to use fire to manipulate landscapes, Homo sapiens was an apex predator unlike any before. The megafauna, which had never encountered such an intelligent and relentless hunter, had no evolutionary defenses. The Toba survivors' descendants reshaped not just human history, but the entire ecology of the planet, becoming the dominant force in every ecosystem they entered. The pattern is too consistent to be coincidental. Continent after continent, island after island, the arrival of Homo sapiens was followed by the disappearance of the largest and most spectacular animals. Africa was the exception, and this exception proves the rule. African megafauna, having evolved alongside hominins for millions of years, had developed a healthy fear of humans. They had learned through countless generations that these bipedal creatures, despite their small size, were dangerous. Elephants, rhinoceroses, hippopotamuses, and the great cats of Africa survived because they respected the threat humans posed and adjusted their behavior accordingly. But the megafauna of other continents had no such education. They had never seen a human before, never learned to associate our scent or our presence with danger. This naivety was their undoing. Australia provides the starkest example. When humans first arrived on that island continent around 50,000 years ago, they found a land of giants. The marsupial lion Thylacoleo was a powerful predator with the strongest bite force of any mammal pound for pound, equipped with huge slashing claws and shearing teeth. The giant, short-faced kangaroo Procoptodon stood over 2 meters tall and weighed nearly 250 kilograms. The Diprotodon, the largest marsupial ever to exist, resembled a wombat the size of a hippopotamus. There were giant flightless birds, massive snakes, and enormous monitor lizards called megalania that reached lengths of 6 meters or more. Within a few, in this 1,000 years of human arrival, every one of these species was extinct. The coincidence in timing is impossible to ignore. The mechanisms of extinction were likely multiple and reinforcing. Direct hunting was certainly a factor. Humans needed protein and fat, and large animals provided abundant supplies of both. A single mammoth kill could feed a band for weeks and provide materials for clothing, shelter, and tools. Even if hunting removed only a small percentage of a population each year, the cumulative effect over centuries would be devastating for slow-reproducing species. Large mammals typically have long gestation periods, small litter sizes, and extended periods of parental care. They cannot bounce back from population declines quickly. When human hunters consistently removed more individuals than could be replaced through reproduction, the trajectory toward extinction was inexorable. Fire was another powerful weapon in the human arsenal. The descendants of Toba had inherited millennia of knowledge about controlling and using fire, and they deployed this technology to transform entire landscapes. In Australia, evidence suggests that humans used fire to clear dense forests, creating open grasslands that were easier to hunt in and that attracted grazing animals. This landscape burning altered vegetation patterns, reduced habitat for fire-sensitive species, and changed the entire ecosystem. Some animals could not adapt to the new fire regime and disappeared. Others found their food sources altered or reduced. The cumulative effect was an ecological revolution, a fundamental reshaping of the Australian environment that persists to this day in the fire-adapted eucalyptus forests and grasslands that dominate the continent. Competition for resources also played a role. Humans did not just hunt large animals. They competed with predators for prey and with herbivores for plant resources. As human populations grew and expanded, they squeezed out other species, claiming the most productive territories and the most reliable water sources. Animals that might have survived human hunting in isolation could not survive the combination of hunting pressure, habitat modification, and competition for food. The ecological space that had supported diverse megafauna communities for millions of years was progressively claimed by one species, Homo sapiens, and its growing entourage of camp followers and domesticated animals. Climate change undoubtedly contributed to these extinctions. The end of the Ice Age brought dramatic environmental shifts, with rising temperatures, changing precipitation patterns, and shifting vegetation zones. But these climate changes were not unprecedented. The Pleistocene was characterized by repeated glacial and interglacial cycles, and the megafauna had survived previous warm periods. What was different this time was the presence of humans. Climate stress weakened populations and fragmented habitats. But it was human hunting that delivered the final blow to already vulnerable species. The combination of natural climate change and human impact created a perfect storm of extinction from which the megafauna could not recover. The extinction of the megafauna transformed Earth's ecosystems in ways that still resonate today. Large herbivores shape their environments, maintaining grasslands, dispersing seeds, cycling nutrients, and creating habitats for other species. Their loss triggered cascading effects that altered plant communities, soil chemistry, and fire regimes. We live in an ecologically impoverished world compared to the one that existed before humans spread across the globe. The descendants of Toba did not just survive their near extinction. They became the most destructive force the planet's ecosystems had ever encountered, reshaping the living world in their own image and leaving behind a legacy of empty niches and vanished giants. The legacy of the Toba bottleneck is written into every cell of every human being alive today. Our low genetic diversity, compared to other great apes, is a permanent scar from that ancient near-extinction event. This homogeneity has profound implications. It means that the concept of race, as a biological category, has no scientific basis. The genetic differences between any two human populations are vanishingly small, surface-level adaptations to local environments like skin color, hair texture, or lactose tolerance. All humans share over 99% of their DNA. We are quite literally a single family, descended from a small group of survivors who clung to life in Africa 70,000 years ago. This genetic unity is both humbling and powerful, a reminder that beneath all our cultural and superficial differences, we are fundamentally the same, shaped by the same ancient struggle for survival. When geneticists compare human DNA sequences to those of our closest living relatives, the chimpanzees and bonobos, the contrast is startling. Despite numbering only a few 100,000 individuals living in fragmented populations across Central Africa, chimpanzees harbor far more genetic diversity than the entire human species. Two chimpanzees from the same forest can be more genetically distinct from each other than a Norwegian is from a Japanese person, or an Australian Aboriginal from a Peruvian. This remarkable human uniformity is not what we would expect for a species that numbers 8 billion and occupies every habitable environment on Earth. It is the signature of a severe population crash, a moment when the vast majority of human genetic variation was permanently lost, leaving behind a species that is, in evolutionary terms, almost clonal. The implications of this genetic uniformity extend far beyond academic interest. They strike at the heart of how we understand human difference. For centuries, humans have divided themselves into races, categorizing people by skin color, facial features, hair type, and other visible characteristics. These divisions have been used to justify slavery, genocide, colonialism, and countless forms of discrimination. But when we examine the genome, we find that these visible differences are literally skin deep. They represent adaptations to local environments accumulated over the past 70,000 years since humans spread out of Africa. a mere blink of an eye in evolutionary terms. Skin color, the most commonly used racial marker, is controlled by a handful of genes and reflects adaptation to different levels of UV radiation. Darker skin protects against sun damage in equatorial regions, while lighter skin allows for better vitamin D synthesis in higher latitudes. These are simple, recent adaptations that tell us nothing meaningful about underlying genetic differences. The genetic variation that does exist among human populations follows a pattern called clinal variation, meaning it changes gradually across geographic space rather than clustering into distinct groups. If you were to walk from Nigeria to Norway, sampling DNA along the way, you would find no sharp boundaries, no clear dividing lines between populations. Instead, gene frequencies would shift gradually, with each village more similar to its neighbors than to distant populations. This pattern is exactly what we would expect from a species that expanded rapidly across the globe and maintained gene flow between adjacent populations. It is completely inconsistent with the idea of separate races that evolved in isolation. The medical implications of our genetic unity are significant. Because we are so genetically similar, we share susceptibilities to the same diseases and respond similarly to the same treatments. A drug that works for one population generally works for others. Organ transplants between unrelated individuals are possible because our immune systems are similar enough to tolerate foreign tissue with appropriate immunosuppression. Blood transfusions work across racial lines because blood types are distributed across all human populations. Our shared ancestry is literally life-saving, enabling modern medicine to treat any human patient with the same basic toolkit. Yet, our genetic uniformity also carries risks. Genetic diversity provides a population with resilience against environmental threats. When a pathogen emerges, some individuals in a genetically diverse population are likely to carry resistance genes, ensuring that at least some survive. Our reduced diversity means we are more vulnerable to a pandemic that could, in theory, affect everyone equally. We carry this vulnerability as a legacy of Toba, a reminder that our species has already brushed against extinction and emerged diminished. Perhaps the most profound implication of the genetic evidence is philosophical. We are one family. Every person you have ever met, every stranger on the street, every face in a crowd on the other side of the world is your relative. We all descend from the same small group of survivors who endured the volcanic winter, who refused to let humanity die, who carried the torch of consciousness through the darkness. The conflicts that divide us, the hatreds, the prejudices, the wars fought over imagined differences, all of these are betrayals of our fundamental unity. The Toba bottleneck stripped away our genetic diversity, but in doing so, it created the conditions for the most profound truth we could ever discover about ourselves. We are not separate races or peoples. We are one humanity, bound together by shared ancestry, shared biology, and a shared destiny on this fragile planet. One of the most critical adaptations that allowed the Toba survivors to rebuild and eventually dominate the planet was language. While the exact origins of complex human language are debated, many linguists and anthropologists believe that fully modern language, with complex grammar, syntax, and the ability to discuss abstract concepts, emerged or was refined around the time of the bottleneck. Language allowed humans to share detailed knowledge about resources, coordinate complex hunts, teach skills across generations, and build intricate social networks. It enabled the transmission of culture in a way that was impossible for other species. Language was the software that ran on the hardware of the human brain, and it turned small, vulnerable groups of survivors into unstoppable information-sharing networks. The ability to say, "There is danger beyond that hill," or "We must move before the rains come," was the difference between extinction and survival. Language is perhaps the most distinctively human trait. Other animals communicate, certainly. Birds sing, bees dance, chimpanzees gesture and vocalize. But no other species possesses anything approaching the complexity, flexibility, and generative power of human language. We can combine a finite set of sounds into an infinite number of sentences. We can discuss things that happened in the past, things that might happen in the future, things that exist only in our imaginations. We can lie, we can joke, we can compose poetry. This capacity is so fundamental to our experience that it is difficult to imagine thinking without it. Language shapes how we perceive the world, how we categorize experience, how we remember and plan. It is the medium through which culture is transmitted and the tool through which societies are organized. The evolutionary origins of language remain mysterious, largely because language leaves no direct fossil record. Vocal sounds vanish into the air the moment they are produced, leaving no trace for archaeologists to discover. What we can study are the anatomical structures required for speech, the brain regions involved in language processing, and the genetic variants associated with linguistic ability. The fossil record shows that the anatomical apparatus for speech, including a descended larynx, a flexible tongue, and fine motor control of the lips and jaw, was present in Homo sapiens by at least 200,000 years ago. This suggests that the physical capacity for complex speech was in place before the Toba eruption. But physical capacity and actual performance are not the same thing. A car engine can produce enormous power, but that power means nothing without a driver who knows how to use it. The crisis created by Toba may have provided the selective pressure that transformed latent linguistic capacity into the fully modern language we know today. In times of plenty, when food is abundant and dangers are predictable, simple communication might suffice. But when the world is in chaos, when traditional knowledge fails, when survival depends on rapid sharing of novel information and complex coordination of group behavior, the advantages of sophisticated language become overwhelming. The survivors of Toba would have been under intense pressure to communicate effectively. Those who could share information about newly discovered food sources, warn others of unfamiliar dangers, describe the location of distant refugia, and coordinate group strategies for survival would have had a significant advantage over those who could not. Language also enabled cumulative culture, the ability to build on the knowledge of previous generations rather than starting from scratch. Each generation does not have to rediscover fire or reinvent tool-making. Instead, children learn from their elders, absorbing the accumulated wisdom of countless ancestors through spoken instruction and demonstration. This creates an ever-expanding reservoir of cultural knowledge that grows over time. The wheel, the bow and arrow, agriculture, writing, the scientific method, all of these are products of cumulative culture, innovations that were preserved and improved upon because language allowed them to be transmitted across generations. Without language, each generation would be limited to what it could discover on its own. With language, humanity became a collective intelligence, a superorganism of knowledge that grew more powerful with each passing century. The social power of language extends beyond mere information sharing. Language creates identity. It binds groups together through shared stories, songs, and traditions. It establishes norms and expectations, defines kinship, and structures social hierarchies. The survivors of Toba, huddled in their refugia, would have used language not just to survive, but to maintain social cohesion under unimaginable stress. Stories told around the fire, myths that explained the catastrophe and offered hope for the future, would have provided psychological comfort and reinforced group identity. Language was the glue that held fragmented societies together when everything else was falling apart. Today, over 7,000 languages are spoken across the globe, each a unique expression of human creativity and a vessel carrying the cultural heritage of its speakers. Yet all these languages share the same fundamental properties, the same underlying grammar, the same capacity for infinite expression. This universality speaks to our common origin, to the shared ancestors who first developed fully modern language in the shadow of Toba and passed it down through generations to every culture on Earth. When we speak, we are using a tool forged in the fires of near-extinction, refined over 70,000 years and shared by all humanity. Language is the Toba survivors' greatest legacy, the gift that enabled all others. What does it mean that we all descend from one small tribe? It raises profound questions about human consciousness and identity. Did those survivors possess something qualitatively different? A spark that set them apart? Some researchers speculate that the bottleneck coincided with the emergence of what we might call full self-awareness, the ability to not just think, but to think about thinking, to imagine the future, to ponder mortality. This metacognition would have been a tremendous survival advantage, allowing for long-term planning and innovation. The artistic expressions, the burial rituals, the symbolic objects that appear in the archaeological record after Toba all point to a people who were grappling with existential questions, who were aware of their own fragility and mortality. In surviving Toba, they did not just save their bodies, they preserved the very essence of what makes us human, our questioning, creative, conscious minds. Consciousness remains one of the greatest mysteries in science. We know what it feels like to be conscious, to experience the world from a subjective point of view, to have thoughts and feelings and sensations that are uniquely our own. But we do not know how this inner experience arises from the physical matter of the brain. How does 3 pounds of neurons, firing electrical and chemical signals, produce the vivid Technicolor movie of conscious experience? This is what philosophers call the hard problem of consciousness. And despite centuries of inquiry, we are no closer to solving it. What we can do, however, is ask when and why consciousness evolved to its present level of complexity, and whether the Toba catastrophe played a role in that evolution. The survivors of Toba were almost certainly conscious in some sense. All mammals appear to have some form of subjective experience, some awareness of their environment and their own bodily states. But human consciousness seems qualitatively different. We do not just experience the present moment. We travel mentally through time, remembering the past and imagining possible futures. We think about our own thoughts, evaluating our beliefs and questioning our assumptions. We wonder about the nature of existence, ponder our own mortality, and seek meaning in a seemingly indifferent universe. This metacognitive capacity, this ability to reflect upon our own mental states, is what distinguishes human consciousness from the awareness of other animals. Did this capacity emerge suddenly, or did it develop gradually over millions of years? The archaeological evidence suggests a significant acceleration around the time of Toba. Before approximately 70,000 years ago, human material culture was relatively simple and static. Stone tools changed slowly, symbolic behavior was rare or absent, and there is little evidence of the kind of abstract thinking that characterizes modern humans. After Toba, the record explodes with creativity. Art, jewelry, sophisticated tools, complex burial practices, all the hallmarks of fully modern human cognition appear in rapid succession. Something happened during this period that transformed human consciousness, and the intense selective pressure of the volcanic winter may have been the catalyst. The emergence of metacognition would have provided enormous survival advantages during the Toba crisis. The ability to imagine future scenarios, to think through the consequences of different choices before acting, would have allowed survivors to plan more effectively for scarce resources. The capacity to reflect on one's own knowledge, to recognize what one knows and what one does not know, would have facilitated more efficient learning and knowledge sharing. The awareness of one's own mortality, while psychologically challenging, would have motivated long-term thinking and investment in future generations. Those who could think about thinking, who could step back from immediate experience and consider the bigger picture, would have been better equipped to navigate the unprecedented challenges of the volcanic winter. Consciousness may also have facilitated the social cooperation that was essential for survival. Understanding that other people have minds, that they have their own beliefs, desires, and intentions, is fundamental to successful social interaction. This capacity, known as theory of mind, allows us to predict others' behavior, to form alliances, to negotiate and persuade. In the high-stakes environment of the Toba aftermath, groups whose members could effectively read each other's minds and coordinate their actions would have outcompeted groups that could not. The selective pressure would have favored not just individual intelligence, but social intelligence, the ability to navigate complex webs of relationships and obligations. The artistic and ritual behaviors that emerged after Toba suggest that survivors were also grappling with existential questions. Why do we suffer? Why do we die? Is there meaning to our existence? These are questions that only a self-aware being would ask. And the answers humans developed, the myths and religions and philosophies that would eventually flourish across every culture, are evidence of minds wrestling with the fundamental mysteries of existence. The cave paintings, the carved figurines, the carefully arranged burials, all speak to a species that had become aware of itself, aware of its place in the cosmos, and determined to make sense of its brief moment of existence. The survivors of Toba bequeathed to us not just their genes, but their consciousness, the questioning, wondering, meaning-seeking awareness that defines what it means to be human. While Toba is the most dramatic candidate for the cause of the human genetic bottleneck, it is not the only theory. Some scientists propose that the bottleneck was not caused by a single catastrophic event, but by the cumulative effects of the Ice Age. The period from 200,000 to 50,000 years ago was marked by extreme climate variability, with rapid swings between cold glacial periods and warmer interglacials. Each climatic downturn would have reduced available habitats and food sources, causing repeated population crashes. Over time, these repeated bottlenecks could have winnowed down human genetic diversity just as effectively as a single mega-disaster. Other theories point to disease, perhaps a deadly pandemic that swept through early human populations, or geographic isolation that fragmented populations and prevented gene flow. The truth may be a combination of factors, with Toba acting as the final, most severe blow to an already stressed and diminished population. The serial bottleneck hypothesis offers an alternative framework for understanding human genetic history. Rather than a single catastrophic crash, this model proposes that human populations experienced multiple smaller reductions over tens of thousands of years. The Pleistocene epoch, spanning from about 2.6 million to 11,700 years ago, was characterized by dramatic climate oscillations. Glacial periods lasting tens of thousands of years alternated with warmer interglacials. And within these larger cycles were shorter, sharper fluctuations that could shift regional climates dramatically within decades. Each cold phase would have shrunk habitable zones, reduced food availability, and pushed human populations toward extinction. Some groups would have disappeared entirely. Others would have survived, but with diminished numbers and reduced genetic diversity. This model gained support from genetic studies, showing that human diversity did not decline in a single sudden event, but rather accumulated reductions over extended periods. When geneticists examine patterns of genetic variation across the genome, they find evidence consistent with multiple bottlenecks at different times. Some regions of the genome show signatures of very ancient population restrictions, while others appear to have been affected more recently. This mosaic pattern is difficult to explain with a single catastrophic event, but fits well with a model of repeated, overlapping population crashes. Each downturn would have eliminated some genetic variants while preserving others, gradually homogenizing the human gene pool over thousands of generations. Disease offers another potential explanation for population crashes. Early human populations, living in small, isolated bands with limited contact with other groups, would have been vulnerable to novel pathogens. A deadly disease emerging in one population could spread rapidly through connected groups, causing massive mortality before burning itself out. Such epidemics have occurred repeatedly throughout recorded human history, from the Black Death to the 1918 influenza pandemic. And there is no reason to think they did not occur in prehistory. Without modern medicine or understanding of disease transmission, early humans would have been helpless against a virulent pathogen. The genetic signature of such an epidemic would be similar to that of an environmental catastrophe, a sudden, severe reduction in population that eliminates much of the existing genetic diversity. Geographic isolation provides yet another mechanism for reducing genetic diversity. The African continent, while vast, contains numerous geographic barriers that could have fragmented early human populations. Mountain ranges, deserts, lakes, and shifting vegetation zones would have divided populations into isolated pockets with limited gene flow between them. Within each pocket, genetic drift, the random fluctuation of gene frequencies that occurs in all small populations, would have caused some variants to disappear and others to become fixed. Over thousands of years, this process of isolation and drift could have significantly reduced overall human genetic diversity, even without any catastrophic population crashes. Some researchers have proposed that all these factors may have worked together. Climate variability during the Ice Age created a stressful baseline condition, repeatedly pushing populations toward their limits. Disease outbreaks periodically culled already stressed populations. Geographic barriers prevented recovery by limiting gene flow between surviving groups. And then Toba struck, delivering the knockout blow to a species already teetering on the edge. In this synthesis, Toba was not the sole cause of the bottleneck, but rather the final straw, the catastrophe that pushed an already vulnerable population past the point of easy recovery. The debate over the cause of the human genetic bottleneck continues, and it is unlikely to be resolved definitively anytime soon. The events occurred so long ago and left such fragmentary traces that definitive proof may be impossible to obtain. New genetic techniques, more sophisticated climate models, additional archaeological discoveries, all of these continue to refine our understanding. What is not in dispute is that a bottleneck occurred. The genetic evidence for a severe population restriction sometime between 50,000 and 100,000 years ago is overwhelming. Whether Toba was the primary cause, a contributing factor, or merely coincidental remains an open question. But the result is the same. We are all descended from a small group of survivors, a fragile band of humans who carried the future of our species through whatever darkness threatened to extinguish it. Could the Toba catastrophe have left a psychological imprint on our species? Some evolutionary psychologists speculate that the near-extinction event may have hardwired certain behaviors and anxieties into the human psyche, Our innate fear of sudden environmental change, our tendency to form tight-knit groups, our suspicion of outsiders, and our drive to accumulate resources and prepare for disaster might all be echoes of a time when survival was never guaranteed. The trauma of Toba, passed down through countless generations, could be the root of our existential anxieties and our relentless drive to control and predict our environment. We are a species that has stared into the abyss of extinction and survived. And that experience, encoded not in conscious memory, but in the very structure of our brains, may shape how we see the world and our place in it even today. The human brain is not a blank slate. We enter the world with predispositions, tendencies, and fears that were shaped over millions of years of evolution. Some of these are obvious, like our fear of heights or snakes, reflexes that protected our ancestors from common dangers. Others are more subtle, like our tendency to see patterns even where none exist, a cognitive quirk that helped our ancestors detect predators in the rustling grass, but now makes us susceptible to superstition and conspiracy theories. These evolved tendencies are not conscious choices. They are the architecture of our minds, built from the experiences of countless generations who survived long enough to reproduce. The Toba catastrophe, if it truly brought humanity to the brink of extinction, would have exerted extraordinarily strong selective pressure on psychological traits. Those whose minds were best equipped to handle the crisis would have survived and passed on their genes. Those whose psychological makeup was less suited to the demands of survival would have perished. Over just a few generations, this intense selection could have significantly altered the average psychological profile of the human species. Traits that were merely advantageous before Toba might have become essential afterward, their prevalence in the population increasing dramatically as carriers out-survived and out-reproduced those who lacked them. Consider our deeply ingrained fear of scarcity. Humans are hardwired to worry about having enough food, enough water, enough resources to survive. This anxiety drives us to accumulate far beyond our immediate needs, to hoard and save against uncertain futures. In the modern world of abundance, this tendency can become pathological, manifesting as greed, hoarding disorders, or the irrational consumption that threatens our planet. But in the aftermath of Toba, when resources were desperately scarce and the future utterly uncertain, this fear of scarcity would have been profoundly adaptive. Those who accumulated resources when they could, who never felt secure no matter how much they had, would have been better prepared for the lean times that inevitably came. Our powerful tribal instincts may also trace back to this period. Humans are intensely social creatures, finding comfort and identity in group membership. We naturally divide the world into us and them, favoring those who share our group identity and viewing outsiders with suspicion. This tribalism can be destructive, fueling prejudice, discrimination, and conflict. But in the context of the Toba aftermath, strong group cohesion would have been essential for survival. Groups that maintained solidarity, that shared resources among members and defended their territory against outsiders, would have out-survived fragmented, individualistic groups. The intense in-group loyalty and out-group suspicion that characterizes human psychology may be a legacy of this time when your group was all that stood between you and death. The human capacity for anxiety itself may be a Toba inheritance. We are a worrying species, prone to imagining disasters that may never happen, to lying awake at night contemplating worst-case scenarios. This tendency causes immense suffering in the modern world, where anxiety disorders are among the most common mental health conditions. But anxiety is fundamentally about anticipating and preparing for threats. In a stable, predictable environment, excessive anxiety is wasteful and maladaptive. In the chaotic, unpredictable world of the volcanic winter, however, those who worried constantly, who imagined every possible danger and prepared for it, would have been better positioned to survive. The anxious minds that plague so many of us today may be echoes of ancestors whose worry kept them alive when complacency meant death. Perhaps most profound is our existential awareness, our knowledge that we are mortal, that our lives are finite, that death awaits us all. This awareness is uniquely human and uniquely burdensome. No other species, as far as we know, lives with the constant consciousness of its own mortality. Some researchers speculate that this existential awareness became acute during the Toba crisis, when death was omnipresent and unavoidable. The survivors watched their friends and family members die, experienced the collapse of their familiar world, and confronted the very real possibility that humanity might not survive. This confrontation with mortality may have catalyzed a new level of self-awareness, a consciousness of death that became permanently encoded in the human psyche. We are a species haunted by the knowledge of our own extinction, and that haunting may have begun in the shadow of Toba. Every ritual, every tradition, every story we tell has roots that stretch back to those Toba survivors. The human impulse to gather around a fire, to share food, to tell stories, to create art, to bury our dead with care, all of these behaviors can be traced back to the societies that emerged from the Bottleneck. These were not primitive brutes. They were us, facing unimaginable hardship with courage, ingenuity, and hope. When you look at a painting, listen to music, read a book, or gather with loved ones, you are participating in a cultural continuity that began 70,000 years ago in the shadow of a volcanic winter. We are the inheritors of their resilience, the living proof that even when reduced to a handful, humanity's fire cannot be extinguished. We carry their legacy in our genes, our cultures, and our indomitable will to survive and thrive. The continuity between those ancient survivors and ourselves is both humbling and inspiring. We tend to think of prehistoric humans as fundamentally different from us, as primitive ancestors who lived in a world so removed from our own that we can barely imagine it. But the truth is far more intimate. The people who survived Toba had the same brains we have. They experienced the same emotions, the same fears and hopes, the same love for their children and grief for their dead. They laughed and cried, formed friendships and rivalries, dreamed of better days and worried about the future. When we look into the eyes of a loved one, when we feel the warmth of companionship or the sting of loss, we are experiencing exactly what they experienced. We are not their distant descendants. We are them, separated only by time. The cultural practices that define human societies across the globe bear witness to this continuity. Every culture on Earth gathers around fires, real or symbolic. The hearth has been the center of human social life for hundreds of thousands of years. And even in our age of central heating and electric lighting, we are drawn to flames. We build fireplaces in homes that do not need them for warmth. We gather around campfires on summer nights. We light candles for celebrations and commemorations. This attraction to fire is not merely aesthetic. It is a deep-rooted connection to our ancestors, to the countless generations who huddled around flames for warmth, protection, and community. The fire that saved our ancestors during the volcanic winter still flickers in our souls. Storytelling is another universal human behavior that connects us to our ancient roots. Every culture tells stories. From the elaborate mythologies of ancient civilizations to the bedtime stories we tell our children. Stories are how we make sense of the world, how we transmit knowledge and values, how we create shared identity. The survivors of Toba surely told stories, tales of the catastrophe they had witnessed, of the heroes who saved them, of the spirits and forces they believed controlled their fates. These stories would have evolved over generations, transformed into myths and legends, passed from culture to culture as humanity spread across the globe. The stories we tell today, though different in content, serve the same fundamental purposes. They connect us to each other and to something larger than ourselves. Art, that most human of activities, also traces its lineage back to the Toba survivors and their immediate descendants. The first known artworks, the ochre engravings and shell beads of Blombo's cave, emerged in the period immediately following the Bottleneck. This was not coincidence. Art is born from the uniquely human capacity for symbolic thought, the ability to let one thing stand for another, to create representations of the world and of abstract ideas. This capacity, refined under the intense selective pressure of the volcanic winter, gave rise to the artistic impulse that has produced everything from cave paintings to cathedrals, from folk songs to symphonies. Every work of art ever created is a continuation of a tradition that began when our ancestors first scratched patterns into ochre stones. Even our treatment of the dead reflects this ancient continuity. Humans are the only species that systematically buries their dead with ritual and care. Archaeological evidence shows that deliberate burial practices emerged around the time of Toba, with bodies carefully placed, sometimes accompanied by grave goods or covered with ochre. This treatment of the dead reflects a consciousness of mortality and a concern for the afterlife, or the dignity of the deceased that is quintessentially human. When we gather to mourn our loved ones, when we place flowers on graves or scatter ashes in meaningful places, we are participating in rituals that stretch back to the very origins of human consciousness. We are not merely biological descendants of those ancient survivors. We are their cultural heirs, continuing traditions and behaviors that have been passed down through thousands of generations. The thread connecting us to them is unbroken, woven through every story told, every song sung, every painting created, every fire kindled, every loved one mourned. They survived so that we could exist. And in living fully, in creating and loving and questioning and striving, we honor their sacrifice and carry forward the flame of humanity that they refused to let die. The story of Toba is not just ancient history, it is a warning. Supervolcanoes still exist today. Yellowstone in the United States, Taupo in New Zealand, and the Campi Flegrei in Italy are all active volcanic systems capable of eruptions on the scale of Toba or larger. While the probability of such an eruption in any given year is low, on geological timescales, they are inevitable. Modern civilization, with its global interconnectedness and reliance on stable climates and supply chains, is arguably more vulnerable to such a catastrophe than our ancient ancestors were. A Toba-scale eruption today would cause immediate mass casualties, collapse agriculture, trigger global famine, and plunge the world into political and economic chaos. Understanding the Toba event is not just an academic exercise. It is a crucial part of assessing and preparing for existential risks that could once again bring humanity to the brink. Yellowstone National Park sits atop one of the most powerful volcanic systems on Earth. Beneath the geysers and hot springs that draw millions of tourists each year lies a massive magma chamber, a reservoir of molten rock that has produced 3 super eruptions in the past 2.1 million years. The most recent of these, 640,000 years ago, ejected over 1,000 cubic kilometers of material, creating the Yellowstone caldera that now forms the heart of the park. While this is smaller than Toba, it was still a civilization-ending event by any modern standard. The Yellowstone system remains active, with the ground surface rising and falling as magma moves beneath. Hot springs shifting and changing, and thousands of small earthquakes occurring each year. Scientists monitor these signs carefully, watching for any indication that pressure might be building toward another catastrophic release. The Campi Flegrei caldera near Naples, Italy, presents perhaps an even more immediate concern. This volcanic system lies beneath one of the most densely populated regions in Europe, with over 3 million people living within its potential blast radius. The caldera has been experiencing a phenomenon called bradyseism, a slow uplift of the ground surface caused by magma or volcanic gases accumulating beneath. In recent years, this uplift has accelerated, accompanied by increased seismic activity and changes in gas emissions. While scientists cannot predict exactly when or if an eruption will occur, the warning signs are concerning enough that Italian authorities have developed evacuation plans for the region. An eruption at Campi Flegrei, even one much smaller than Toba, could devastate southern Italy and affect climate and agriculture across Europe and beyond. The modern world's vulnerability to a supervolcanic eruption is paradoxically greater than that of our ancient ancestors. The survivors of Toba were hunter-gatherers, living in small mobile bands that could relocate to more favorable areas and subsist on whatever resources they could find. Modern civilization is built on foundations of stability, interconnected supply chains, just-in-time manufacturing, global trade networks, and agricultural systems that depend on predictable climate patterns. A volcanic winter lasting even a few years would shatter these foundations. Crops would fail across entire hemispheres. Food reserves, which in most countries amount to only a few months of supply, would be exhausted rapidly. Transportation networks would be disrupted by ashfall and fuel shortages. Economies would collapse. Governments would struggle to maintain order as populations faced starvation. The cascading effects of such a catastrophe are difficult to fully imagine. In our interconnected world, a disaster in one region quickly becomes a global crisis. The COVID-19 pandemic offered a small preview of how vulnerable our systems are to unexpected disruptions. A supervolcanic eruption would be orders of magnitude worse. The initial death toll from the eruption itself, while potentially in the millions for a densely populated region like Campi Flegrei, would be dwarfed by the deaths from famine, disease, and conflict in the years following. Some researchers estimate that a Toba-scale eruption today could reduce the global population by 50% or more within a decade, not from the eruption itself, but from its secondary effects. What can be done to prepare for such an event? The honest answer is that complete preparation is impossible. No amount of planning can fully mitigate the effects of a global volcanic winter. However, certain measures could reduce the severity of the catastrophe. Maintaining strategic food reserves, developing cold-resistant crop varieties, investing in indoor and vertical farming technologies, and creating robust emergency response plans could all help humanity weather the storm. Perhaps most importantly, continued research and monitoring of active supervolcanic systems could provide early warning of an impending eruption, giving populations time to evacuate danger zones and governments time to implement emergency measures. The lesson of Toba is ultimately one of resilience. Our ancestors faced a catastrophe that should have ended our species, and they survived. They did so through ingenuity, cooperation, and sheer determination. If we face a similar challenge in the future, we will need those same qualities, amplified by the knowledge and technology that 70,000 years of cultural evolution have provided. The story of Toba is not just about what happened in the past. It is about what might happen in the future, and about our responsibility to prepare for the unthinkable. If there is one lesson to take from the story of Toba, it is this: we are one. The divisions we create based on nationality, ethnicity, religion, or ideology are insignificant compared to the fundamental unity written in our DNA. We all descend from the same small group of survivors who faced annihilation and prevailed. Every person you meet, no matter how different they may seem, is your distant cousin, sharing the same ancient lineage. This knowledge has the power to reshape how we see each other and the world. In an age of conflict and division, the Toba story is a reminder of our shared fragility and our shared strength. We are the children of survivors, and our survival in the future depends on recognizing that we are, and always have been, one human family. The genetic evidence is unequivocal. Every human being on Earth today shares a common ancestry that stretches back to a tiny population of survivors who endured the volcanic winter approximately 70,000 years ago. The variations we see among populations, the differences in skin color, facial features, hair texture, and body proportions, are superficial adaptations to local environments that accumulated over the relatively brief period since our ancestors spread across the globe. Beneath these surface differences, we are remarkably, almost identically, the same. The genetic distance between any two humans is far smaller than the genetic distance between two chimpanzees from the same forest. We are not different races or subspecies. We are one species, one family, one blood. This biological unity stands in stark contrast to the divisions that characterize human societies. Throughout history, we have divided ourselves into tribes, nations, empires, and ideologies, often defining our identities in opposition to others. We have fought wars, committed genocides, enslaved millions, all based on perceived differences that have no meaningful biological basis. The categories we use to separate ourselves, categories of race, ethnicity, and nationality, are social constructions, invented by humans for human purposes. They are not carved into our genes. The science of human genetics has revealed an uncomfortable truth for those who would divide us. There is no scientific basis for racism, no genetic justification for treating any group of humans as inferior or superior. We are all cousins, and the family resemblance is overwhelming. Understanding our shared ancestry has profound implications for how we approach the challenges facing humanity today. Climate change, pandemic disease, nuclear proliferation, artificial intelligence. These are threats that affect all of us, regardless of nationality or ethnicity. They are global problems that require global solutions, cooperation across borders and cultures, a recognition that we share a common fate. The Toba survivors understood this, perhaps instinctively. They knew that their survival depended on working together, sharing resources, and supporting each other through the crisis. The same is true today. The problems we face are too large for any one nation or group to solve alone. We need the collective wisdom, resources, and effort of all humanity. The story of Toba also offers hope. If our ancestors could survive a volcanic winter with nothing but stone tools, fire, and each other, surely we can face the challenges of our own time. We have technologies they could not have dreamed of, knowledge accumulated over thousands of years, and the ability to communicate and coordinate on a global scale. What we sometimes lack is the will, the recognition that we are in this together, that the fate of each is bound to the fate of all. The Toba story can help provide that will. It reminds us that we have faced extinction before and prevailed. It reminds us that our diversity is a recent overlay on a fundamental unity. It reminds us that cooperation, not conflict, is the key to survival. In a world that often seems fractured beyond repair, the message of Toba is one of connection and solidarity. Every human being you will ever encounter, every face in every crowd, in every corner of the world, is family. The person you disagree with most vehemently, the stranger who seems most foreign and incomprehensible, the enemy you might be tempted to hate, all of them carry the same genetic legacy as you. All descend from the same small band of survivors who refused to let humanity perish. We are united by the deepest possible bond, the bond of shared ancestry and shared survival. Recognizing this unity does not erase our differences or our conflicts, but it places them in perspective. Our divisions are recent and shallow. Our unity is ancient and deep. The survivors of Toba did not know they were saving humanity. They were simply doing what all living things do, struggling to survive, to find food and shelter, to protect their families and communities. But in doing so, they preserved the human lineage for all future generations. We are their legacy, their gift to the future. And we honor them best not by fighting over the scraps of a divided world, but by embracing our common humanity and working together to build a future worthy of their sacrifice. We are one family. It is time we started acting like it. And now, the final revelation, the second cliffhanger promised at the beginning. The Toba catastrophe and the genetic bottleneck it caused did not just nearly destroy us. It made us. The extreme selective pressure, the necessity for unprecedented cooperation, innovation, and cognitive flexibility, forged modern humans in a way that no gradual evolution could have. Without Toba, we might still be one of several competing human species, unremarkable primates on an unremarkable planet. Instead, we became the lone survivors, the innovators, the storytellers, the species that would one day leave footprints on the moon. The tiny African tribe that almost became all of us did become all of us. And in doing so, they transformed a fragile band of refugees into the most powerful force on Earth. We are not just the descendants of survivors. We are the inheritors of a miracle, the living legacy of the day humanity refused to die. Consider for a moment the extraordinary improbability of your existence. The volcanic winter could have killed everyone. A slightly more severe eruption, a slightly less resilient population, a few more years of cold, and the human experiment would have ended before it truly began. The universe would have continued without us, without art, without music, without love, without wondering about the stars. But against all odds, a tiny group of humans held on. They faced the impossible and refused to surrender. They adapted, innovated, cooperated, and survived. And from that small band of survivors, from that improbable remnant, came everything. Every civilization, every culture, every scientific discovery, every work of art, every act of kindness and courage. All of it flows from those few thousand souls who refused to let the fire die. The crisis of Toba acted as an evolutionary crucible, burning away everything that was not essential and forging what remained into something new. The humans who emerged from the bottleneck were not the same as those who entered it. They had been transformed by the experience, not just culturally, but genetically. The intense selection pressure had favored the most adaptable, the most cooperative, the most cognitively flexible. These traits, concentrated in the surviving population, became the defining characteristics of our species. The cognitive revolution, the explosion of art and symbolic thought, the development of fully modern language. All of these may have been consequences of the bottleneck, emergent properties of a population that had been refined by fire. Without the bottleneck, the trajectory of human evolution might have been entirely different. Other human species, the Neanderthals, the Denisovans, Homo erectus, might have persisted alongside us, competing for resources and territory. We might never have developed the cognitive edge that allowed us to dominate the planet. We might have remained one primate species among many, intelligent but not exceptional, successful but not world-changing. Toba, in nearly destroying us, may have been the catalyst that made us who we are. The catastrophe that almost ended humanity may have been the very thing that made humanity great. This is the profound irony at the heart of the Toba story. Our greatest near-death experience was also our greatest transformation. The volcanic winter that should have been our extinction was instead our crucible. We entered it as one species among several, anatomically modern, but behaviorally unremarkable. We emerged as something new, something unprecedented in the history of life on Earth. We became the storytellers, the dreamers, the builders of civilizations. We became the species that would one day look up at the stars and wonder, that would decode the secrets of the atom and the genome, that would create beauty and meaning in a universe that offers neither by default. The footprints left on the moon in 1969 are a direct line from the footprints left in the African dust 70,000 years ago. The same species that huddled around fires in the volcanic winter, struggling to survive, eventually stood on another world and looked back at Earth. That journey, from near extinction to planetary dominance to space exploration, is the story of humanity. It is a story of resilience and creativity, of cooperation and competition, of tragedy and triumph. It is our story, the story written in our genes and passed down through 100,000 generations. When you look in the mirror, you are seeing a survivor. When you hold the hand of a loved one, you are touching a cousin. When you create something beautiful or solve a difficult problem or help a stranger in need, you are honoring the legacy of those who came before. We are the children of Toba, forged in fire, tested by catastrophe, and transformed into something miraculous. We carry within us the spark that refused to die, the flame that has burned continuously for 70,000 years and will continue to burn as long as humanity endures. The tiny African tribe that almost became all of us did become all of us. And now, knowing what we know, understanding where we come from and what we survived, we face the future not as strangers divided by trivial differences, but as family united by the deepest possible bond. We are one humanity, one story, one flame. And that flame, kindled in the darkness of a volcanic winter, will light our way to whatever comes next.